All right. Hi, everybody. Good morning, good afternoon, good evening, maybe online. Welcome to FAccTRec 2023, the sixth iteration of this workshop at Recsys. And there we go. All right. First, introducing to you the organizing committee for this year. We've got Michael Ekstrand over here. We've got Jean Garcia Garthright, she's online. We've got Nassim Somboli, she's also online. Amifa Rash, I think she's also online, yep. Yes. And I'm Caroline Dinesen. And we've also got a steering committee that was really helpful this year. Robin Burke is walking around somewhere here in the building. We've got Pierre-Nicolas Schwab. Don't know if he's online, might be. We've got Toshihiro Kamshima over here, working very hard on that everything's going correctly online as well as here in person. And we've got Luca Belli. And then for a little bit of history, this workshop started at Recsys 2017 in Italy. And it has been there every year except 2019. But there was a related workshop at SIGAIA that year in Paris. And, well, we're very happy to be back and be here in Singapore hybrid this year. And I see already that there's a 2024 iteration happening. So we hope to see you all there again. And we are also part of the ACM Facts Network. And if you want to find more information about that, they have a website as well. So it's not only in the Recsys community, but also broader. Then if you want to stay connected, we've been discussing a little bit how to do this. We still are on X, which used to be Twitter, but we've also added a Mastodon. We are on the Recsys Slack, #responsible. And we also have a LinkedIn group, which is called Socially Responsible Information Access. So if you want to reach out to us or reach out to any of the authors, feel free to do that here. Of course, there's also the website that you might have seen already that's dedicated to this workshop. And there will also be links to the papers and links to the videos later if the authors are okay with us sharing their video. Then on themes, we are deliberately broad, as the slide says, because this is a topic where the community really needs to give input on what it should entail. But what we see falls under our workshop at minimum is responsible recommender systems, fairness, accountability, transparency, compliance, and safety as well. Well, yeah, like I said before, the work doesn't stop here at Recsys. There's other conferences as well, because this is a very important, these are very important themes and topics that should be talked about as broadly as possible. Right, and now I'm handing off to Michael for the
So as we've done for a while, we have a few different types of papers here. So we welcome both position papers, and we welcome as well research papers that present empirical results or any kind of research results. We also welcome a kind of paper that we have never really gotten very many submissions of experience reports, which is basically, we actually tried to do this, and here's what worked or what went wrong that maybe doesn't have the kinds of research methods that we usually see in a research paper, but provides a report on what actually happened and, say, trying to do responsible recommendation in production. If you are in that space and would like to submit such a paper sometime, we want those. We just never get very many of them. But we want, with the position papers, we're looking for broadly a couple of kinds of things. New ideas and proposed directions of where responsible recommendations should be going, kinds of things maybe that we aren't thinking about that we should be. And then also reflections, as I said, the reflections on practical issues, or retrospective kinds of things of taking stock of where research in this line of work has been going over the last few years. And then research papers that provide empirical results, analytical results, both quantitative and qualitative. And again, these are very broad in scope in terms of what we're looking for, anything under this broad banner of social responsibility and recommendation. Because as Caroline said, like the issues and the topics really do need to come from the community, not just like, oh, we made these 3 boxes and that's what counts. No, we want to leave room for new questions that maybe we haven't thought of, especially as we move around the world. The papers at FAccTRec are non-archival. So, and this is very deliberate. So like the papers are not formally published in the proceedings. We asked all the authors to stick them on archive or somewhere similar and give us a link. And there's a couple of reasons for this. One is to facilitate, like to really focus it on conversation and discussion and sharing of ideas, not just as a mini conference kind of workshop, but like we've had papers that are presented here that were already published in a full conference proceeding somewhere, but it's valuable to bring them to the attention of the community here because you might not read the details of the KDD proceedings. But then also on the other side, that's much more common, for this to be a space where we can present and talk about early stage work and get feedback on it so that then authors can take that feedback and when they submit a revised and expanded version of the paper to the Recsys technical program or to SIG-IR or to FACT or somewhere, it's the best that it can be. And to give like this environment to try out the ideas, get the first round feedback, and then send them to a formal publication. So it's very deliberately non-archival so that we can have it fill those kinds of roles for the community. This year we had 16 submissions. It was down a little from last year, not entirely sure why, but of those we accepted 12, 6 long and 6 short papers that will be presented today, 9 of which are research papers and 3 of which are position papers. And so we had each article reviewed by at least 2 reviewers. You can find the articles, all the articles. There's one actually that I'm still waiting for the link on. But except for that one, all of the articles are available on the FAccTRec program page on the FAccTRec website. And thank you very much to our program committee for doing this review labor that enabled us to select the excellent program that you're going to see today. This wouldn't work without their help and contribution and feedback to the authors. It's the chat. Okay. So today's schedule. We have a lot going on today. So this is the opening session. So we've got the welcome, which we're giving you right now. And then we have an opening keynote from Rashad Motra, who I'll introduce shortly. Then session 2 is going to be our first presentation of papers, and those to reduce the logistical hassles of switching back and forth between whether we're in person or remote. We've kind of clustered the sessions. So the second session is going to be a sequence of remote presenters of the various research papers and position papers being presented. Session 3 will be all on-site presenters. And session 4 will be a mix. It's going to start with virtual presenters, and then it's going to close with one more on-site presentation and our farewell and discussion and conclusion for you. We hope you will stay for all of it or for as much of the day as you can. The session schedules are slightly weird because the breaks are longer and than a lot of times. We don't have 90-minute sessions with half-hour breaks. So this first session's 90 minutes, then we have a 45-minute break for coffee, and then an 80-minute session, followed by lunch, another 80-minute session, and then a 90-minute session to wrap up the day. Our long papers are going to be 20 minutes presentation plus 5 minutes questions. If you're presenting, we do ask that you keep on time so we can have time for questions and discussion. The whole feedback on early stage really works best if we have time to get those questions and that feedback. Then the short papers will be 10 or 12 minutes of presentation and then the questions. So questions and feedback. So if you're on Zoom, you can type your questions in the Zoom chat. You can probably type it in the Q&A. Q&A is turned on, but I'm not entirely sure how that works. So try it. If we don't see your question, mention it in chat. If you're in the room, you can open up Zoom and type your question into the Zoom chat. The link is in the Recsys Hub. Or during the question time, we will have microphones that we can bring around, and you can ask your question that way. And that works for both the virtual and the in-person talks. The session chair will manage the stream of questions from both sources. And please do give questions and constructive feedback on how we can, especially for the early stage stuff that is going to really help the authors, the questions that can help the authors can think about as then they revise and build on their work. We're recording the presentations. We're going to cut the Q&A out so that not everyone in the room has given us permission to stick their question on YouTube. So but we are recording it, and for all of the authors who did give permission for their talk to be published, we will be providing that video after the conference after we get a chance to edit them. If you are presenting on site and I do not yet have your slides, please email me your slides. Because plugging in and out many different laptops is a pain. We're going to be running all of them from my laptop in on-site sessions. So please email me your site. Oh, that's the wrong email address. Well, that email address will get to me. mbxstrand@drexel.edu is the best one. So, okay. I don't know why I typed that email address there, but that one works. It gets to me. But that's the schedule for today, and look forward to seeing all the talks. And I first encountered Rishabh's work with a paper that he did on auditing search engine performance across demographic groups on Bing. And my first published work on fair recommendation was directly applying his search paper and basically saying, what Rishabh did for search, let's go try to do that for a recommender system and an offline evaluation. He's then done a lot of work on various aspects of multi-stakeholder recommendation. While at Spotify, he did work on modeling and providing equitable benefit and quality across diverse sets of stakeholders and balancing interests in multi-stakeholder recommendation systems. And he's now at ShareChat, where he is, if I'm going to get his title correct, Director of ML Engineering, I think, and is going to be talking with us today about stakeholder outcomes as we look to serve the next billion users with recommendation.
Thanks, Michael, for the introduction. I know a bunch of people. This is an amazing audience to be presenting this talk at 2:30 a.m. UK time. And again, this is my natural hours because before I got married, this is the times I was actually pretty active mentally. So the title of today's talk is going to be Design Choices and Stakeholder Outcomes in Multi-Stakeholder Recsys. And first of all, a few disclaimers, also a bit of personal news. Sad to miss the in-person workshop. I really wanted to be there at Recsys, but then I kind of sought permission from my wife and it got declined. Honestly, we have a newborn and we have a small baby. She's 12 weeks old and it just couldn't find the motivation to kind of step out right now. But also this is an overview of a few different topics from the lens of differential impact, especially in a marketplace realm. And a bunch of these are personal opinionated views, some backed by scientific research, some backed by personal opinions, some backed by my recent experiences in an industry in the current macroeconomic world, which we live in since the last couple of years, right? So a lot of this is going to be very kind of guided by a lot of practical challenges, especially in the Asian countries as well, wherein we start looking at recommendations, we start looking at large user bases, a lot of heterogeneities, but from a lens which is very different than the systems which have been built for Western audiences in general. So a lot of this is going to be motivated also from a revenue perspective, from a scale perspective, which is going to be, again, we're going to see examples on why they may or may not make sense in different places. So quick background, I was at Spotify until last year looking at marketplaces. and my PhD work was with Dr. M. Yilmaz on search ranking. And since then, I've been working mostly on recommendations. So we're going to be talking about 3 different aspects, and I want to keep the talk at max of like 40-45 minutes because I'm hoping I could get some feedback. We could have a lot of open discussions on some of these topics. And the overall point which I want to bring forward is the amount of decisions which are seemingly minor, which could have a lot of butterfly-like ripple effects on these platforms. And we're going to focus on multi-stakeholder platforms. So I'm going to talk about first why user-centric feeds are suboptimal and just kind of drive home the point that we should start looking at multi-stakeholder systems as one of the most prominent systems which are being developed and start re-looking at the existing systems from that multi-stakeholder lens as well. Once we establish that for the first 10 minutes, I'm going to talk about some design choices. And I want to bring in a different scenario view of it and talk about like different stakeholders and present a couple of examples. And towards the end, I want to talk about like a few more practical sessions, practical lessons and discussions. So the first point I want to convey is like, hey, consumer-centric feeds are suboptimal, right? And the question which I want to start with is like, is caring about the user enough? So I grew up looking at working and using like Bing and Google, and most of these were like user-centric engagement, looking at user satisfaction, like differential impact on users, fairness on users angle, caring about user metrics, caring about user engagement and everything about user, right? But then if I start looking at a lot of these applications we start consuming right now, including Spotify, including Netflix, including Airbnb, Uber, Deliveroo, Uber Eats, Swiggy, Zomato, all of these companies, right? I mean, they do have to care about the user, but also the delivery partner, also the restaurants, also the suppliers. And most importantly, they have to care about the platform economics, right? Because again, right, the company has to survive and the company has to make enough money in order to kind of keep the lights on. So what does that mean, right, for us? And what does it mean for the design of these recommendation systems? So the high level point over here is that we will be stepping in from going from like just optimizing for user-centric goals towards optimizing some multi-objective goals, right? And I can have user-centric, supplier-centric, platform economics, a bunch of different stakeholders which are going to be varying across different platforms. But then the entire point is that, hey, I mean, right now, if I'm only thinking about like everything from a user lens, and why not broaden the lens and look at multiple stakeholders? Now, there are reasons why why a consumer-centric feed is suboptimal, right? There's like user behavioral modeling reasons, and there are also system design reasons. I'm going to focus a bit more on the user side and slightly just hand wave the system angle to it. But then if I start talking about user behavior, right? I mean, there's a lot of user-led heterogeneity, right? User behaviors are directed by intents, right? On the Spotify homepage, you might have different intents. If you're using Pinterest, you might have some specific, some more specific, less specific, short-term, long-term intents. And essentially users also have different traits, right? I mean, some users are very narrow in their consumption behavior. Some users are a lot more diverse. We're going to talk about this slightly in more detail in later on as well. But then like users have different traits. And we've seen like across platforms, right? On Reddit, on Spotify, that diverse listeners are better. I mean, they convert more to premium. They churn less on the platform. And also like in general, diversity helps the platform as well. Because if you're consuming diverse content, then maybe the platform can show you some tail creators, some like tail suppliers or some strategic content, and then maybe you're okay with that. So, I mean, so there's a consumption diversity angle. The other point to mention is user needs are generally malleable, right? I mean, some users come into the platform with a very, very specific need. Some users are like me. I mean, hey, I just want relaxing music. So maybe you can recommend me a bunch of different music. I'm not really looking for a specific song, right? And then also like not just in a session or a query basis, right? I mean, there's a long-term trajectory wherein users move around these genres, these interest profiles, these tastes, and then like you can start guiding and nudging these trajectories as well. And importantly, right, users have different tolerances to distortions and receptivity, right? Some users want discovery, some don't. Some users are okay with getting some tail creators, some users are not, right? So again, like we want to look at what sort of like tolerances and propensities users have, and then kind of make decisions accordingly, right? I mean, if users like discovery, then great, let's facilitate discovery to them. If they don't, then maybe let's step back and focus more on familiar music or like familiar content. But the overall point over here is looking at the user's intents, looking at the user's consumption behavior, looking at the user needs being malleable, looking at like different sorts of propensities and tolerance of the user. The crux of it all is that there's a lot of fluidity in user needs. So maybe there are opportunities on these platforms wherein the system can take a decision on the user's behalf. And importantly, right, I mean, use this malleability to shape and influence the consumption on the platform, right? Because what I want to do is like, in a multi-stakeholder world, I do want to make sure that it's not just that the users are ending up happy and satisfied, but then my creators are happy as well. My suppliers are happy as well. My delivery partners on Uber Eats are happy as well. My platform economics also is sustainable, right? So the overall point is like there's enough user level heterogeneity for me to exploit that and shape consumption in like more meaningful and multi-objective ways. Now, another related point over here is that if I just blindly optimize for consumer relevance, I mean, we have a lot of evidence from a lot of published work and like in production systems that just blindly optimizing for consumer relevance is going to hurt supplier exposure, right? And we all know that like superstar economics, like long tail problems are pretty common in search and recommendation systems. But importantly, right, I mean, if the moment I start looking at not just two objectives, but other stakeholder objectives as well, we start seeing the amount of trade-offs which exist, right? I mean, if you look at on the left, if I expose certain data creators and if I plot them against user satisfaction, then there's a variety of design choices I can make, right? Do I want to be kind of optimizing more for users, less for tail creator gains, or on the right hand side, right? Do I want to focus more on like popular content, less popular content, and what sort of satisfaction ranges do I hit accordingly, right? Now in a multi-objective world, the important point over here is that mathematically, right, using machine learning, we can find out the Pareto optimal curve probably, right? But then where in that Pareto optimal curve do I want to be situated, right, as a platform is a business strategic decision, right? Because again, quarter on quarter, week by week, month over month, there's going to be different business needs. And then maybe at some point I do want to kind of bank in more revenue because my quarter is ending. And then I'm going to move myself to a slightly different point on that Pareto curve. So again, this is where like different trade-off exists, and I want to be able to control where I land. And essentially, right, I mean, we want the models to be able to learn all of this, right? We want models to learn which users should I push more video content to, right? Which users should I use for more ads versus less ads? How do I make the matching? Like, I mean, which creators are going to be forming a great relationship with users? Which users would want to follow these creators? How do I grow the audiences of a specific creator? And what sort of trade-offs are healthy for the long-term sustainability, right? So there's a lot of these like problems which I don't want to happen like just because, right? I mean, I want to design systems which are able to extract a lot of value out and then do a bit of like value creation, not like value extraction, wherein I'm kind of removing something from stakeholder over and giving to somebody else, right? Maybe there's a lot of scope for value creation possible on these platforms, right? So this is where like there are enough reasons around the user behavior, around the user modeling, around the user expectations, which maybe hint us that, hey, maybe just focusing on user is slightly suboptimal, but then we can look at a broad holistic sense of not just users, but also the other stakeholders and be more inclusive in our model design. Now, there's a bunch of system design reasons as well. And again, I'm not going to go into details of that. Just a few of them are mostly around you don't want to overburden the core ranker. And more importantly, you want the stakeholders to have control of their own fate, right? That the success of the creator should be in their hands. The success of the content providers should be in their hands, right? I mean, it should not be that, hey, the ranking system you have is the bottleneck for the other stakeholders, and they're not able to kind of drive their destiny on these platforms because my recommendation system was like designed in certain ways, right? So how do I democratize innovation and develop these like modular pieces which can all come together and create my feed? And more importantly, in a practical scenario, I do want to provide these levers to my leadership, right? That, hey, I mean, as business owners, you do want to manage these trade-offs, and then you want to kind of exert your preferences based on the business needs and then steer the platform in that direction, right? So this is where the overall story starts coming in together, that there's a lot of behavioral aspects around user level heterogeneity, trade-offs between user and creator goals, user and other stakeholder goals, the amount of trade-offs possible, and wanting the model to learn all of this together and do more value creation, right? So this is where the underlying point over here is that platforms have enough leeway to shape consumption on their platforms and shape it in a way which benefits not only the users, but also the creators, the suppliers, the delivery partners, and the platform economics itself. So that's the view behind why I think like the multi-stakeholder lens is one of the most promising lens to look at across these multiple platforms, right? I mean, a lot of these like billion-dollar companies, hundreds of millions of users using them, they all can be like recast from a multi-stakeholder lens. So that's where we are, right? I mean, we are now kind of trying to form this picture that there's a user, there's a supplier, there's a platform. We want to do this balancing. There's going to be some feedback. There's going to be some adaptive decisioning. I want to do all of this, create the final feed, get the evaluation, and then have the feedback loops. And then this entire ecosystem starts working together. right? I mean, of course, this, again, I'm preaching to the choir. It's not just about one model. It's about an ecosystem of models, ecosystem of design choices, which interact together to make an application serving hundreds of millions of users across hundreds of millions of creators work at this scale, right? So this is where, once it works, it starts kind of putting in the content and user flywheel. Because again, right, I mean, the moment user starts liking content, the creator becomes excited. Hey, I'm getting a lot of engagement on this content. Maybe I should start creating more of this content. And then they start kind of fine tuning their creation process, and they create more, they create better content. The users like it. So these platforms want to establish these content and user level flywheels so that the entire marketplace, the supply demand, can start kind of kicking off one after the other, right? So just before we wrap up the marketplace lens, right? I mean, I just want to high level mention that there are different aspects about user preferences, creator preferences, and content preferences, which these systems should care about. On the user side, we want to make sure that what sort of value do users derive from the platform? Are they kind of discovering content? Are they finding meaningful creators? What are their intents? How tolerant are these users? Can I inculcate habits in these users? I want to understand user dissatisfaction. I want to look at user LTV, that what's the value of this user for me? And again, right, I do want to make sure that I retain high LTV users. And if there are low LTV users, then how do I extract value from them? So there are these multiple angles from which, again, right, to view users on a platform. If I start talking about creators, then there are different goals for creators, right? I mean, some creators are like that, hey, give me 10,000 new listeners, right? I mean, I'm on TikTok, I want 10,000 new followers. But some people are like, hey, I'm a creator, I don't want 10,000 followers, give me 100 fans. But these 100 fans should be able to buy my merchandise, right? And these are very different goals. I mean, as a creator, I might be on a very different journey than other creators, right? So there's going to be a variety of creator goals, which these companies and applications should be mindful of. Now, from a platform perspective, right, I could have goals around specific creators that, hey, I mean, let's say I signed up a deal with one of these like amazing creators and I want them on a platform. I do want to retain them on my platform. So these are goals which I can take on a specific creator. Or I can take a step back and say that, hey, I want to grow my middle tier of artists or middle tier of creators. So then it's not just about specific creators, but then like I do want to take on this goal of beefing up my middle class of creator economy, right? And then there's going to be a lot of interaction across these creator outcomes. There's going to be a creator journey optimization, wherein I want to estimate which creators are benefiting from my platform, which creators might churn, how do I retain them, and make sure that the creators are having successful journey on the app, right? And more importantly, right, which are the strategic creators for me on a platform, right? Even if you look at like these educational apps, right? I mean, there's going to be some people teaching some courses which are going to attract a lot of listeners, right? A lot of educated audiences. Now, these are strategic creators which the platform will go after, right? So how do we understand the strategic value of these creators is also another angle. So we talked about like some user angles, some creator angle. There's a lot around content as well, right? I mean, there's a strategic distribution of content. Like Netflix has these Netflix originals versus like a Disney and Marvel movie, right? And there's going to be conflicting goals. That should I show another platforms like Disney and Marvel movie on my homepage versus my original? And there's going to be a balance which I'll have to strike, right? Because again, based on contract, I'll have to pay out that money to these other platforms if the users are streaming that content. And then, I mean, there's a lot of problems around like the category health, that looking at the tail categories, looking at how they're performing, and overall, right? I mean, what sort of distribution do I want on my platform? So there's a bunch of like content angle over here as well. And importantly, right, I mean, they all start coming together finally, right? That there's not just user, there's not just creator, there's not just content, but there's user-creator relationships around the fan funnel. That, hey, is this user exposed to this creator? Have they discovered it? Have they become a fan? Are they going to buy the merchandise? Are they going to attend the concerts? So there's a fan funnel there. From the creator side, right? I mean, we want to look at how do we grow the creator audiences. On the creator content front, there's like a lot of topics around feedback loops for creators. That should this creator be creating content in category C1 versus C2? How much supply is enough for a certain category? How many creators are enough for a category? And then on the user content side, looking at the supply demand, right? In a literally content marketplace, looking at both the supply and the demand is going to be critical. So this is where the entire problems around users, creators, content, and their relationships together start forming the bedrock of what does it take to kind of design these multi-stakeholder recommendation systems at scale. So that's a quick summary. I mean, that's literally like 12 minutes of establishing that, look, there's a lot of design choices. There's a lot of aspects around the creators, around the content on an application, around the users, and how they all come together to create a meaningful content marketplace. Now, this is where what I want to do next is, with this background, I want to start looking at some of these pieces bit by bit, right? And then mention that, hey, while doing this, right, I mean, we're going to end up making some design choices which might have insane differential impact across my users, across my creators, across my content, and on my platform. And to drive the point that, look, we want to be mindful of these choices, and it's not just about fairness and accountability on the user front, but then like in this marketplace, it's about accountability and fairness on the entire stakeholders, right? On the set of entire stakeholders. So this is where, right, what we're going to do is we're going to look at 8 scenarios, maybe like 2 to 3 minutes on each scenario. And we're going to start with like the user front, couple of scenarios on the creator side, couple of scenarios on the content side, and a couple of scenarios on the platform side. And the template we're going to follow for each of them is going to be this. We're going to pick up a scenario. I'm going to establish the background. I'm going to establish a design choice which a system engineer would make. And then what kind of impact which we have seen in production systems by making that design choice, right? So this is typically what we want to do. And we want to start by looking at the user side and then take examples on each of these stakeholders. So great. So let's look at the user side, right? We're going to talk about consumption diversity first. So the background over here is that if you look at the Spotifys of the world, the Netflix of the world, or any of the other like Uber Eats as well, you're going to see these grid-like scenarios wherein you want to populate the homepage, right? And what I want to do is like, I want to be able to personalize these recommendations via bandits. So again, this is a common problem which people face that, hey, I want to drive user engagement on the application, right? And a background over here is like, I do know that based on some past work, I do have different types of users on my app. I mean, there are certain users who are specialists, and they're going to only consume content in a small specific category. There are certain other users who are generalists, and they're going to consume content in a wide variety of categories. Now, what I want to do is, I want to be able to design these models which work great for specialists and journalists and all other types of users. So again, right, in one of the papers we had at Recsys earlier, we designed a contextual bandit model, which is just going to optimize for one user engagement objective, which could be playlist streamed. Now, again, right, I mean, the details of the exact models we're not going to talk about them. But once you design these models, right, you're going to sample these playlists and start creating the homepage, which is fine. You're going to talk about the reward as well. The reward could be if the user streamed a playlist for more than 30 seconds or more than X seconds, it's a +1, great. The bandit did a great job. If not, maybe like it's not great and I'm not going to reward you. So this is typically like how any of these engineers are going to be designing these models for the feed. Now, this is where, right, I mean, we've just established that before we start looking at the impact, let's just make sure that we understand that, hey, there are different types of users, and certain users are more specialist, certain users are generalist. And the way we define specialists and journalists could be different, right? I mean, here in this work, we just used the users' diversity of consumption. So what we're going to do is like we have these embeddings of the items users are consuming, and then we can look at the average cosine similarity between the consumed items and the user center of mass. And that will give me a way of defining the user's consumption diversity in general. And the finding which we found was that we saw a lot of differential impact across different users, right? I mean, especially across journalists versus specialists. So we observed that diverse users are likely to churn a lot more, right? I mean, diverse users will churn very, very differently than non-diverse users. So here is a plot, right? I mean, on the x-axis, we plot the GS score. So if you're on the left, you have more diverse consumption. If you're on the right, you have less diverse consumption. And what we saw, and the 0 is the global churn rate, right? Churning is like you stop using the app after X weeks. So what we saw was that there was a 25% decrease in churn as and when users' consumption become a lot more diverse, right? So if you start looking at the moment you go from the right of the plot to the left, right, you start decreasing. And what that means is your probability of churning from the app starts decreasing. And that happens even if we control for activity, right? I mean, the percentiles of the activity are also, I mean, right? I mean, we can control that if you're less active versus more active, the trend remains the same. So the point over here is that we start seeing that if we design a simple recommendation system, bandit-based recommender system, we deploy it in production, and then we look at like how it's performing, then we start seeing that, hey, if users are consuming diverse content, then they're churning a lot less. And not just churning less, but they're also converting to premium a lot more. And again, at any of these apps, you're going to define conversion to premium as like, is a user converting from a free user to a premium user, which is going to pay X dollars per month for the services. And again, right, I mean, if I look at 0 baseline as a global conversion rate, And if I start plotting it, then we saw that, hey, there's a 30 percentage point increase in conversion if the user starts spending more time in consuming diverse content, right? So even if we control for activity, more diverse users are far more likely to become premium members. Now, this is very interesting, right? Because we start seeing a very big difference between how specialists and journalists behave on a platform. So generalists, which are going to consume diverse content, they're less likely to churn and more likely to convert to premium. But the important point, which was a very important takeaway for us, was that the platform's programming is a lot less diverse than users' organic consumption. Now, this is a very minor looking English statement, but it has a huge implication on a platform. Because if you look at any of these music or Netflix or any of these movies apps, right? I mean, there's going to be recommendations and there's going to be content which I myself search and add to my library. Now, the evidence we found was that the programming from the platform is going to be less diverse than users' organic consumption. And let's look at it, right? If on the x-axis, I plot the organic similarity. That means if things are on the left, they're more diverse, things are on the right, they're less diverse. Now, on the y-axis, I plot program diversity, program similarity, right? So things at the top are going to be less diverse, things at the bottom are going to be more diverse. So now we want to understand that how is users' organic diversity related with their program diversity? Is the recommendation system making them consume less or more diverse content, right? Versus what they would do on their own organically. So again, right, I mean, I can just put a point over here. And for example, over here, we see that the users organically would consume, like, would have a different score, and versus programming, this will be different. Now, just this, the explanation over here is like just a straight line with a 45 degrees will be equal, right? And anything above, their organic streaming is a lot more diverse. Anything below, their programming streaming is a lot more diverse. So that's the way to interpret the plot we're going to put. Now, this is what we found, that users' organic consumption is a lot more diverse than their programming conversion. Now, this is where things above the y is equal to x-axis means that their organic streaming is more diverse. What that means is, and if you link with the point we mentioned, right, that users who have diverse consumption, they're going to churn less and convert to premium more. And we found evidence that, hey, I mean, their programming is apparently less diverse than their organic consumption. So then that means the models are not optimizing for the platform's benefit, right? I mean, you want users to churn less and you want users to kind of convert more to premium subscribers, but then our programming is not fulfilling those needs, and then users' organic consumption a lot more diverse. So this is where, right, I mean, you start seeing that if you have a recommendation model which is trained for a specific user engagement objective, then it's going to have a differential impact across journalists and specialists, and it's going to try to kind of, it's going to maybe like not satisfy users' consumption diversity, and that might impact users' like conversion and churn behavior on the app, right? And these are models which do not specifically account for diversity in general, right? I mean, these are objectives wherein if you just try to optimize for time spent or the number of items you're consuming, then this is what might end up happening. Now, let's look at another realistic scenario more from my recent experiences at ShareChat. Now, again, right, I mean, in the last year and a half, there's a lot of revenue pressure on companies, right? So the goal is to show more ads, right? I mean, how do we increase revenue? We increase revenue by showing more ads on the feed to users, right? I mean, while maintaining user satisfaction. So that stands for satisfaction. Now, one of the solutions which we ended up deploying was that, hey, let's predict users' fatigue score. Fatigue is a proxy for churn, that are users getting upset and annoyed with our recommendations? Maybe there's a chance the user might end up abandoning the app. And then let's try to make that prediction. And once you make that prediction, let's personalize the number of ads we show based on this fatigue score, right? Now, this is a very seemingly a nice heuristical, simple ML model, which typically companies would end up doing, right? I mean, each of these companies do face this challenge, that how many ads do I show? Should I show more ads? Should I show less ads? And how do I personalize that, right? A simple personalization approach could just be based on users' churn probabilities, right? And then you start doing that, right? I mean, let's make a prediction about how likely is the user about to churn. Are they fatigued? And based on that, if they are about to churn, maybe I should scale back. I should step back, show less ads. If not, then maybe I can step in and show more ads, right? So then this is like a one sort of like personalization policy. And we saw big impact across here, right? I mean, we saw that now you have a policy in production which is showing differential ads across users, right? Certain users are shown a lot more ads than other users. And this is based on their current fatigue scores. And this is where the user experience starts fluctuating a lot. right? I mean, if right now we make a prediction that you have a low churn probability, we're going to start showing you more ads. And because we start showing you more ads, maybe your fatigue increases, your churn probabilities increases, and then we show less ads. And this kind of cyclical kind of process kicks in. And this is bad. Why? Because we are very short term, right? In this particular approach, it's a again, right? I mean, this is one of these approaches which an engineer would take and like try to deploy and then get some gains. But then this would create problems. Why? Because certain users are penalized a lot more than other users. And more importantly, right? Somebody's doing that for ads. Now imagine a big org, right? I mean, there's like 100 million users using this app. Probably you're going to have like a lot of product teams, a lot of engineering teams. The ad team started using fatigue score for ad load balancing. Now tomorrow somebody wants to say that, hey, I have this new product. Maybe there's an audio chat room and I want to show that more. If you start doing that, what's stopping the other product teams from using the same score? Now suddenly, right? I mean, because of your prediction about a user, ads team is trying to show more ads. The audio chat room team is trying to show more audio chat rooms. And then all the other users, all the other teams are going to be personalizing in this way. And then we're going to overburden the user with more promotions, more new products, more advertisements, more sponsored content, right? Now, this is where things become bad, right? Because now, based on a prediction, practically you're going to start making these predictions and everybody's going to leveraging it. Where is the centralized control? Right. And especially again in big companies and even like smallish companies, it's very hard for teams to coordinate and then like have a centralized orchestrator, which is going to decide, hey, you've done enough, maybe let's step back. So I think these are some of the other practical challenges which we start looking at it from a user lens. Why? Because in a company, you have to make more money, you have to earn, you start showing more ads, you have to grow these, let's say a new product. I mean, if you launch a new playlist, you'll have to start growing it, right? If you have a new product like chat rooms, you have to start growing it. You do need users, which will make you go from like 1 million daily active users in this product to like 10 million daily active users. So which users you end up targeting is guided by some of these models. And then they start kind of polluting the same set of users, which becomes suboptimal. So these are a couple of examples from the user side, right? Let's step into creators. Now, a typical problem which a company faces is that we want to recommend tail creators, right? Because again, there's a problem that you're going to, you want to surface content and playlists which are not just relevant to users, but also they're going to expose a diverse set of creators. And this is a typical problem which not just music, but also movies and a lot of other companies will face. Now, the important point over here is that if you just plot a playlist fairness across these suppliers and relevance, then the problem is there's nothing on the top right? I mean, there are very, very few playlists or maybe like very little playlists which are both fair to creators and relevant to users, which is going to be a problem because had there been something on the top right, then great. I mean, I would have started showing those sets to users and then my job is done. But it's not there, right? I mean, so then that means there's a trade-off. And this is where what you will end up doing is you're going to end up designing a solution which is going to trade off relevance and fairness. Right? I mean, fairness is a loosely defined term over here. It could just, again, right, you can define what fairness means for you. In this work, we ended up defining fairness as, are we picking up playlists which are created from many, many different creators, right? Are we over-indexed on the top artist and only creating playlists on them? Or do we have some top artists, some middle tier artists, some tail artists, and then my set recommendation is from a heterogeneous set of artists, right? So then, I mean, you can define these functions. One specific function we ended up defining was a submodular function. Now, this is where, right, I mean, if I have to create a set, I'm going to create a set which picks up 2 of these red balls, 1 pink ball and 1 green ball, right? I mean, because that score is under root of 2 plus 1 plus 1, which is 3.414, right? Versus just picking up all 4 from red, which is going to be 2 plus 0 plus 0, which is 2, right? So if I just optimize for this function, it's going to pick up more from, again, it's going to pick up representative examples from each of these different color balls. Now, this is very similar to how you want to select from the different maybe popularity buckets, different quantile buckets, different distribution of these creators on your application. And then this is how we define that, hey, are we diverse in our creators or not? So again, what's the problem? The problem is I want to optimize for relevance and exposure diversity, and I can start trading them off, right? I can have a function which optimizes for this. And I can also try some user adaptive policies because we've just seen that, hey, user tolerances are a thing. So maybe if I'm user aware, I'm going to make better decisions. Now, this is where, right, when we start doing that, then you start seeing that there are some good trade-offs possible. So on the x-axis, we plot where is the policy? Is it policy focusing on the recommendation policy focusing on more relevance or more supply diversity? On the y-axis, we have user satisfaction. Now, if you, again, right, I mean, of course, if you're on the far right, you're going to maximize satisfaction. If you're on the far left, then you're going to optimize for supply diversity, but then it costs you user satisfaction because we see a nice drop, right? I mean, the max and min on the y-axis is a big delta. But then there are these inflection points wherein you can get maybe the best of both worlds. You can get enough supply diversity without hurting the user satisfaction a lot. And this is where we found that, hey, if you're doing this on a personalized level, that certain users are okay with this diversity, certain users not, then maybe you're going to get the best of both the worlds. So this is where, right, I mean, the kind of questions which start popping up are, to what extent do we want to push the users, right? I mean, now we start seeing that, hey, the trade-off exists, and I can maybe get certain gains on the other objective without too much hurting on the user objective. But then on a per user basis, like how much do I push, right? I mean, how much of an exploitation I would end up doing on a per user basis? And more importantly, am I even tracking that? Because these results are on an aggregate level, right? That, hey, in aggregate, you're okay. But then who's looking at the quantile differences? It's not just about the aggregate metric. Who's going to understand and quantify and bring to attention that, hey, the last 10th percentile of users are much worse impacted. And then maybe we should not do that. Or you're repeatedly penalizing certain set of users, and that's bad. On the other side, right, you want to do that to push tail creators, but then what's the way of deciding which tail creators do we want to push, right? I mean, from a platform perspective, do you want to be prescriptive? Now, this is a very important problem which we have faced for the last 2 years, almost every week. Do we want to be prescriptive as a platform, right? Should this creator succeed? Should this content succeed? Should this category succeed on my platform? Where do we stop being prescriptive? Where do we let the models or the user preferences guide us, right? So this is where, like, I mean, some of the practical challenges are around where do we draw the line? When are we being too prescriptive? But I mean, as a platform owner, I want good content to succeed, right? But this is a very easy English statement to make, but the practicalities of it are like nightmarish to solve, right? Because at the end of the day, right, there is some prescriptiveness which you will encode in your systems, and then that becomes bad. Taking a step back, right? I mean, you talked about tail creators. Let's make it a bit more on middle class creators, because again, right, this long tail problem is pretty much everywhere. And again, right, in the influencer culture, in the creator economy, like people do care that, hey, I only have like a small set of mega celebrities which have like 1 million follower plus, but then I have this like long tail wherein I have a bunch of macro, bunch of nano creators who have like very, very small audiences. Now, this is where what I want to do is, as a platform, I want to focus on the middle class and how can I grow my middle tier creators? And this is where, right, I mean, this is coming in from this paper we had at Wisdom, and we ended up trying a reinforcement learning model. What we want to do is like, hey, I want to, again, a very high level reinforcement learning model is I want to learn a policy that gives me a probability of sampling a track given a state S. Now, in this model, right, I mean, I want to explicitly encode the content distribution ask, because I do want to make sure that my distribution is more geared toward the middle tier of artist. So then I throw in a term, right? I say that, hey, relevance, when I'm designing the reward model for this RL model, relevance is important, but also at the same time, this diversity is important. But then, like, I mean, we end up multiplying diversity by relevance because just diversity is not useful, right? I mean, I can just randomly pick up random artists and then that's diverse, but that's not useful. So I do want to make sure that the diversity I enforce is also relevant. So then we do a multiplying with relevance as well. Now, again, right, I mean, let's just kind of high level look at the details of this model. What we ended up doing was we said that, hey, let's look at the user session, summarize the session. Let's look at the last bunch of user sessions, get a dynamic user embedding, and get this dynamic user embedding into a feedback model, and finally use this feedback model in the RL sampling model, right? I mean, the details of this are not as important in this context, but then this is a in-session personalization aware ranker, which is looking at the last few sessions of the user and then trying to make a sampling decision. Importantly, the sampling decision is based on both relevance and my content diversity as well. Now, this is where, right, I mean, when we start doing it on the platform, then we start seeing that, hey, this is great. I mean, we go from this orange distribution to this blue distribution. What that means is my consumption on my application shifts. It shifts slightly towards the middle class artist. And it becomes, again, right, it's not flat at all, but then it becomes more flattish, right? So the relative flatness of my distribution starts increasing. Because again, right, I mean, you see the pink curve of the content distribution slightly goes down and starts kind of beefing up on the lower popularity as well. So the point over here is that we start giving more exposure to middle class creators if you start using some of these like reward balancing techniques in an RL setup. Now, the question over here is like, hey, at what cost, right? I mean, how does it impact the head and tail? Because again, right, I mean, it's a value extraction phrase over here. Because again, if you're giving more exposure, your views on the application are limited. You're going to take away view share from certain set of creators and give to something else, right? And again, the specific question comes in that which middle creators should we focus on? I mean, there are teams in these companies which are dedicatedly focusing on the middle tier of artists, right? But then one of the questions which they will end up facing is that what in these middle class, is any subset of these middle tier artists okay for us? Or do we want to focus on a specific, or do we even want to focus on this specific, right? And the question is like, when do we stop? Now, this when do we stop is a very, very wide question because again, right, I mean, the point over here is what is the ideal distribution which we might want to have? And do we even want to have an opinion on that? Or do we just let the consumption shape that for us, right? So this is a question which we keep coming back to, that, hey, let's give more exposure, but to what extent, right? I mean, where is the view share calculations happening that this is a nice target distribution for us to end up in? But because again, right, I mean, that is very hard for anybody to quantify. And again, right, I mean, maybe there's no point in quantifying that, right? I mean, and we just kind of let the system play out. So again, we've looked at a couple of problems on the user side, right? I mean, we've talked about consumption diversity. We talked about, hey, I want to look at user tolerances when I show more ads, less ads. On the creator side, we've talked about, let's push some tail creators, or let's kind of beef off my middle tier creators. Let's switch to content. Now, these two content examples are rather new because we've talked in the industry, right? I mean, a lot about users and also creators, but one of these things which have been slightly missing from the mainstream has been the focus on content, especially the content lifecycle. And we have some work from our teams coming up in this. So this is a topic which is just focused on content lifecycle, right? And if you look at TikTok, right, or Reels, you have a lot of short videos getting uploaded each month, right? On the apps I work on right now, Share, Chat, and Merge, we have like more than 1 million short videos uploaded each month. Now, this is an insane amount of content getting uploaded, right? I mean, let's take a step back. Let's look at Netflix and the video apps. The video apps have like close to 50,000, 100,000 movies overall. Let's look at the music app. Music apps have 100 million music tracks in the last 200 years of humans creating digital music. The moment you start going from movies to music to short videos is an insane catalog size. Why? Because you have 100 million each month, right? So the amount of corpus available is orders of magnitude higher than music, right? And like tens of orders of magnitude higher than movies. Now, in this world, when I have like close to 100,000, 200,000, 500,000 items every week, how do I bootstrap such fresh content, right? I mean, this freshly uploaded content has 0 views right now, or very, very limited interaction data. Now, let's look at the video apps, right? In video apps, my content has quite a few views because maybe like only a few movies get released every week. So most of the data, 99% of the data I work with in the movie recommendation setting is rich with interaction data, right? Because it's very less is new. Versus in a short video app, most of your content you're working with has barely been around for like a few days or a few hours, right? Now, one of the things which all of these companies do face is bootstrapping this content, right? What do I do? I mean, I don't have the embedding. I mean, literally, right? My ranker needs embedding of this content. This video was just uploaded. My embeddings are based from 2-tower model or some FFM model, which is based on user interacting with it. I have no user interacting with this content. How do I get the embedding? How do I make recommendations in my ranker when I don't even have an embedding for this piece, right? Now, to this, what companies end up doing is they provide min views. Min views is something called minimum views, that we're going to guarantee that, hey, for each post, I'm going to maybe give 100 views or maybe give 50 views. So what one of the design choices, which is at least in production in 2 to 3 companies I'm aware of, is that, hey, let's guarantee that each post gets to at least 50 views, let's say, or 80 views or 100 views, right? And this is where, I mean, you start collecting this user interaction data in order to kind of get some embeddings, in order to learn more about what this content is, and then so that it can go on in this own life cycle, right? Now, this is important. Why? Because I have zero behavioral data and I do want to kind of make some good recommendations. So right now we end up using some sort of content understanding, right? You're going to pass some of these videos to vision transform models, get an embedding, start using them. But then you're waiting for that behavioral data to come in, because at the start, when the content is uploaded, you only have content understanding, zero views. That means zero behavioral embeddings. But then at view 100, view 1000, view 10,000, I have a lot of behavioral data. Now the behavioral embeddings take over, and then maybe content understanding is not adding too much value. At the start, I only have content understanding, I have zero behavioral data. So again, right, the point is to bootstrap this content, people end up giving min views. Now this is, and again, right, I mean, this is one of the like aha moments I had in the last couple of quarters, that for system reasons, I mean, for some weird system engineering challenges, which again, right, we're going to write a blog post about this, not all content are able to get min views quickly, right? I mean, there's some delays, some leakages happening in these indexes, maybe some feedback loop is missing, or maybe you're just kind of matching process is suboptimal. So because of many reasons, not all content ends up getting the min views very, very quickly. Now, this severely impacts the content progression. What that means is if you have certain videos which are getting this minimum views, they're proceeding on to get 1,000 views, 10,000 views, 100,000 views. But for some reason, if because of some system discrepancy or some budget reasons, some of these videos don't end up getting these mini views, then they're not proceeding, right? I mean, they just die out in like 80, 100, 150 views. They don't even get 2,000 views. Now, this is where we saw some amazing results, right? We're yet to kind of fully understand the extent of what's happening. But then we see that posts that receive the full quota of min views within X hours, they go a lot farther, right? The probability of them getting 100 views is 7 times more likely to get 100 views than if they did not achieve the min views quota, right? Same, at 1,000 views, the probability of a post which got all the min views, the probability of that reaching 1,000 views is 15 times more likely to happen than if it didn't get the min views quota fulfilled, right? And same, right? I mean, 170x more likely to get to 10,000 views. Now, this is a very important thing because this literally has a downstream impact on the platform level content distribution. Because certain posts, because of system reason, because of your suboptimal choice of min view allocation, they don't get the quota of min views. We don't end up learning enough behavioral embeddings for them. And then these posts die out. They don't die out because they are not good. They die out because of system design reasons or because of your min view allocation reasons. And more importantly, different categories of content are impacted very, very differently, right? I mean, this is just one example. On the x-axis, we show that how much time does it achieve to get min views. An example over here is if I decide that, hey, every content will get 50 views no matter what. How long does it take for me to get 50 views? That's on the x-axis. On the y-axis, we plot what's the probability of this post getting to 1,000 views if I guarantee the 50 views are given. Now, we start seeing amazing differences across categories as well. That again, right? I mean, something like news, if it doesn't get the minimum views very, very quickly, then the probability of it getting 1,000 views is like decreases exponentially, right? But certain other categories like literature, it's more or less stable. And we start seeing some nice results. That there's a lot of heterogeneity across categories. Some categories are a lot more reliant on content bootstrapping, like news has to be there. Literature, on the other hand, it doesn't matter. I mean, the probability of reaching 1,000 views is more or less stable, regardless of whether you give those initial views quickly or not. Now, this is where, right? I mean, the question over here was, none of this was intentional on our side. I mean, we just said that, hey, we're going to give these min. This is a design choice we made. We're going to give min views. I'm going to make sure that every post gets 50, 80, 100 views. And that's it. But then we start seeing that, hey, I mean, there's a lot of these content level differences which end up happening. And this is where, right, some categories thrive on the platform and some don't. Now, the overall point over here was that whether or not you get min views, that has a huge platform level content distribution impact. Suddenly, if you live in a month of this world, after a month, the content distribution on your application is going to be very, very different than counterfactual content distribution, right? And that's going to be pretty bad. Now, another example, especially in the content world, is how do you define whether the user successfully watched the video or not, right? I mean, there's a lot of content heterogeneity. If you look at YouTube, there's some short videos like 5 seconds, 15 seconds. There's some medium videos like 1 to 5 minutes. There's some long videos like 5 minutes, 20 minutes, 30 minutes. Now, how do you decide a label over here, right? How do we define that? What is the label to train a ranker or a candidate generator? Now, some simple thing I can do, like in search, right? People said 5-10 years ago, if you click on a search result, if you stay there for like 15 seconds, then that's a +1. I think you liked it. You like the result is relevant. Otherwise, it's 0, right? So again, we can have a fixed threshold, or I can have a percentage watch. That if you watch 50% or 90% of the video, maybe you're happy. But the problem here is that these are bad, right? I mean, let's say if you have a 50% or 90% threshold for success, suddenly, right? I mean, it's much easier for you to get 90% watch time in a 30-second clip, because people are gonna like watch it for like 27 seconds. But then if you're looking at a 10-minute clip, 90% of that is like 9 minutes. Very, very few people are gonna watch the 9 minutes of a 10-minute video. So a simple threshold of, let's say, 90% is gonna create a lot of negatives, very few +1s for longer videos, but then a lot of +1s for shorter videos. Same for 20-second threshold, right? I mean, 20-second threshold is gonna focus more on long videos. Now, this is where, right, suddenly your labels are very, very biased. Now, labels are biased based on the video duration. Why? Because the way we define these labels were not debiased using the video duration. Now, this exactly kind of ends up having, again, a platform level distribution effect, right? Suddenly my labels are biased towards one type of video, which are shorter or longer. And because these labels are biased, the models, the candidate generated models I train, they are biased towards shorter or longer videos. And then this kind of percolates on the platform level as well. Now, these are a couple of examples on how some minor design choices can end up impacting the overall content distribution in the app. Now, let's look at a couple of examples on the platform side. On the platform side, we talked a lot about balancing multiple goals, right? I mean, balancing users, user engagement, discovery, balancing middle-day creators, balancing promotional content. And this is where, right? I mean, balancing rewards in a multi-objective manner is something which companies end up doing. And one of the functions people end up using is a generalized uni function, right? I mean, this function has a nice property that it tries to balance the reward. I mean, there's a Bayesian delta principle which says that if you do a gap diminishing transfer from someone with more to someone with less, it's going to decrease inequality in the system, right? So again, if on the rightmost plot, you see that the objective 3 is doing really well, but then if I take something from 3, give it to 2, then it's going to slightly balance out my rewards. So this is a function which obeys this property, right? For again, right, in a multi-objective world, each of my vector x is, let's say, 3 dimensions. If I'm doing really well on 3rd dimension, if I take something away from 3rd, give it to the 2nd, then it's going to increase the overall function value. So that's a nice property of these GGF function. Now, these, we can solve them by solving a linear program, but then they're not scalable. So then we decided to adopt a gradient descent approach. The point over here is that in a setup wherein you want to balance multiple objectives, here is a function which gives you this nice balancedness aspect, right? And then you can put this in a contextual bandit model. That you have this contextual bandit model, the objective function of that model could be multi-objective. And this is what we ended up doing, right? And again, the results were great because we saw that you're trying to minimize the regret of a multi-objective function. And we saw evidence that it need not be a zero-sum game. We can get gains in some of the other objectives without using on the user-centric objectives. But the important point over here was handling the second order effect is very, very hard, right? What happens if a user abandons a session? I mean, the user comes in, I provide them a multi-objective feed. And this is where, if things go bad, then I don't know, right? Who do I blame? How do I attribute dissatisfaction? Where's the feedback loop? How do I penalize different stakeholders? So again, right, I mean, unintended consequences are hard. But more importantly, one of the biggest problems, which again, right, we haven't solved it yet, is how do you make a ship decision? Literally, right? I mean, each change is going to impact all the other stakeholders. What trade-offs are allowed? What trade-offs are preferred? Imagine being a product manager, being an engineer, and facing this dilemma. I have 5 objectives. I have 5 rankers. Which ranker do I ship, right? Let's say the ranker 3 gives me a 23% gain in supply metric. Great. But then it's neutral on long-term satisfaction, maybe 1% on satisfaction. Ranker 5, on the other hand, gives me not 23, but 15% gain in objective supplier, but then a 4.5 to 4% user satisfaction gain, right? I mean, again, right? I mean, how do you make a ship decision when you have multiple objectives involved? Now, this is a very hard problem, which most of these companies are facing on a day-to-day basis. And this is where, right? I mean, formulating this governance comes in, that what metrics are important, in what order of priority, how do we compute them? How do we provide like lower limits that you cannot go below this, you cannot go above this? All of these kind of talk about the governance, which is how do we make ship decisions in a multi-objective world? And this is where like offline evaluation, offline-online correlation, extremely hard. How do we handle long-term impact? How do we kind of manage these expectations across stakeholders? How do we kind of take some objectives from some stakeholder, give it to others? I think these are all practical challenges which not even ML engineers, software engineers on day-to-day basis are facing. And I think like we lack proper methods of making multi-objective ship decisions in these companies. So again, right, I mean, the point over here is that each decision impacts all stakeholders, and we have very limited experimentation, shipment, governance, all of these angles around available for the industry to kind of take a shot at it and like adopt it internally. So overall, right, I mean, what's my point? Looking at these scenarios, the point is there's a lot of design choices, right? A lot of decision choices across the entire Recsys stack, focusing on the users, focusing on the content, focusing on the creators, focusing on the platform, in the candidate generator, in the representation learning, in the ranker, in the multi-objective system. And they start having a lot of unintended ripple effects on platform-wide metrics. And this is where, right, I mean, these scenarios point out that there's a lot of learning to be done, right? I'll just end in a couple of minutes talking about the major learnings, especially in the current world wherein the macro is very different. The first point is the affordability of thinking about these fairness aspects in a platform, right? If you're a startup, you have to survive, right? You have to care about user engagement. And then once the users are engaged, you have to care about revenue, because again, we're going to have revenue goals. And then maybe you start focusing on creator success, retention, then maybe content fairness, right? So there's going to be a journey. And what is the cost of each of these interventions? What is the ROI? I think this is where we need better techniques and more easy adoption of quantification of harm at each step, right? Because maybe there's a software engineer unintentionally making a label decision on short videos versus long videos that will have an unintended consequence on platform level metrics, right? Are they equipped to tackle these problems in a good way, knowing that the impact of their minor decision is going to be platform level content distribution, right? So again, my point is not everybody is super aware, and the quantification of harm is like pretty hard to do, especially if you're not coming in from the FAccTRec community, right? I mean, unintentional consequences are literally everywhere. The other question is establishing this process in companies. Why should one care? What should one care about? And how should one fix it, right? This is where you start providing the incentive that why do you want to prioritize this, right? What are the business incentives? And once you motivate them, then bring in the observability that this is what should be fixed, this is who is impacted, this is how we want to prioritize it, and these are the intervention, right? This literally closes a feedback loop. It's not just about identifying the problems around fairness and accountability and transparency, but here are the solutions, here is how you should fix it, and here are some good and quick and easy integrations. Another thing, especially in the current macro, is being prepared for handling revenue pressures. Again, right, we ended up deploying a bandit model, but then the moment you have to show more ads, you throw out that bandit and then you go like slot. Hey, I mean, I can just, because again, I want to increase revenue in the next 2 months because again, right, the company's survival is at stake probably, and then you're going to end up replacing these bandit models by heuristics. What's the point? The point is, whatever model we end up deploying, making sure that they are controllable very, very quickly and adaptable to the business needs is very important. And this is where, right, you start designing scenarios. How do you treat high RP users differently than low RP users? And how do you kind of manage the different stakeholders across different business needs? And finally, the most important point is the need for developing these deep observability and monitoring technologies to catch these unintended impact from seemingly minor decisions across the Recsys stack, right? Because again, if you have an app which is being used by 200 million users, you'll have like 50, 60 people working on these. Not all of them will be equipped to think about the platform level implications of their minor decisions. How do we as leaders in this industry enable the minor decision makers to understand what the impact could be, how the integration should be done, how do we kind of intervene, how do we solve for it, how do we avoid facing these problems is going to be an important challenge for us to take on.
Okay, so hi, as the person sharing who I cannot see just said, my name is Jennifer, and today I'm presenting Fairness versus Personalization towards Equity and Epistemic Utility, and this is joint work with David Danks, and we're both based at UCSD. Okay, so basically the amount of relevant content available, as we all know, has grown massively, and personalization in recommender systems specifically poses one way to navigate it. So across applications like e-commerce, search engine results, and social media, what we want to do is provide efficient, relevant, and personalized content recommendations. And the challenge here is to do them fairly and accurately, particularly with respect to what we frame as epistemic harms. And we define this as non-deliberate asymmetrical relations that exclude persons from social participation, leading to an intellectual or moral harm. And we'll get into this a little bit more in our paper. So the key contribution of our work here is that we develop the inherent tension between group fairness and personalization. We provide a philosophical argument for fairness and epistemic harms, and we shift from fairness as it targets an outcome to an equity-based universal baseline access to service, and provide policies to operationalize such ideas. So, woof, that's vague. I'm going to break it down into smaller parts. So the first thing that we do here is that we develop the inherent tension between group fairness and personalization. So with personalized recommendations, in non-personalized recommender systems, they're more about finding and treating similar users similarly. So this can be based on user-specific or item-specific profile attributes for similarity. Personalization, here we go. Personalization, however, is fundamentally about treating each individual in distinct ways, where the goal is not to give the same output to each individual, but rather to tailor the outputs to their specific situation. However, personalization has been shown to contribute to echo chambers and radicalization, even when we consider quote-unquote fair re-rankings or fair kind of deployments. Purely on the technical side, we must consider the broader socio-technical system in which factors like domain specificity, recall, and attention affect how users retain and accept or reject information. In addition, there are often very few control or feedback mechanisms, meaning when served an undesired recommendation, how do we correct it? This means there are a few methods of quote-unquote recourse or the clear actions to take to obtain the desired prediction. So to ground this in something concrete, consider two users, each with a search query that's disambiguated by clues to personalization under a query such as like best movie. So what are some of the ways in which we might disambiguate it, and how do we make sure that we do so fairly? So some of the key questions here would be fair relative to what? To each user, groups of users, just like the keynote was talking about. Do we do items or groups of items, and how would you group them? One way may be based on the final distribution of ads for the movie, so that might be like half go to Barbie and half go to Oppenheimer. But I think we can do a little bit better than that. With personalization, we can leverage other information like interests, hobbies, age groups, other things like that. We might even consider defining fairness in terms of bigger picture things like broader exposure and cultural relevance of these movies, such as themed or inspired workouts, memes, reaction videos, and outfits. And that's how the epistemic harms or the epistemic injustice part ties in, where it can be beyond just the explicit like knowledge of the item, but also the cultural relevance and the broader expanse of the downstream effects of this. So what we want to do is determine how to ensure fairness in this context. Should it be proportional to the rate at which people are truly interested in things like Barbie and Oppenheimer? Or how do we differentiate the influences of recommending content to users and their subsequent interest, as opposed to serving them content that is already aligned with their interests? So in the related work, there are a couple of things that people have considered historically. So that might be individual fairness, which requires a domain-specific similarity function, which is often hard to determine and takes a lot of time and resources. Group fairness, so examples might be disparate exposure, visibility, or utility. These are each different definitions, but all of these require sensitive attributes. And what are these sensitive attributes actually trying to get at is how do we compare similar kind of groups of people or users? And that may be based on what they value. And so that might be informing your kind of disambiguation process. And that's how you're trying to treat them similarly. And we'll delve into that a little bit more. And then calibration doesn't require sensitive attributes, but it can contribute to hegemonic regimes of representation in things like news. So then what do we pose as kind of the solution here? We look at this, so we explicate this like core tension here, For things like group fairness, when we have sensitive attributes that are required, this can be problematic because they're coarse proxies for values. For example, when you treat groups, minority groups as monoliths, you treat them as a homogeneous other, often centering kind of like a single kind of neutral or like historically like neutral default, which is problematic in many senses. Alternatively, Kong 2022 considers an intersectional approach, and they explicate how historically the fairness community has applied intersectional approach as either choosing specific subgroups of sensitive attributes, which can be problematic because then how do you pick? Do you just choose like race and gender? What does that exclude, like disability and other things like that? And then if you consider the combinatorial grouping, the combinatorial grouping of all of the possible sensitive attributes, this faces kind of practical data limitation problems. Alternatively, instead of requiring sensitive attributes, if you condition on something like user search history, this underdetermines values, as multiple sets of values and interests could be consistent with identical search histories. This is also noisy from things like when you don't search, like when you don't explicitly search for things that are like your core values, or the inability to know things like situational demands or motivation. Some examples of this would be things like third-party questions for like a homework, or if someone asked you a question and you end up Googling it, devil's advocate versus supporting arguments. And then finally, it's also temporally unstable. Starting from the same starting point, there may be infinite paths in which people can diverge, which makes temporal guarantees difficult. So now that we've seen this inherent tension with kind of like historical ways in which people have defined fairness, next what we do is we look at fairness in terms of epistemic harms. And so I'll next define what that means. So epistemic utility is the value or usefulness of information in terms of improving knowledge, understanding, or beliefs. It is the intrinsic value of acquiring knowledge and understanding, the role of information as a valuable resource for intellectual growth, social mobility, and production. And it captures the motivational value of information for people's behavior. So what it does is that it captures a lot more than just was I exposed to this item or not, or do I know of this item or not? It guides our decisions and what to believe in particular situations. It also has downstream benefits of enhanced decision-making, prediction, problem solving, and overall intellectual development. So conversely, the like lack of epistemic utility then is framed as epistemic injustice or epistemic harms, particularly as a lack of access to information. So for example, for an alternative product, that might be something like, without knowledge of a better alternative product, an individual may be purchasing a needlessly expensive product. Without lack of an understanding of a concept or language phenomena, such as racial discrimination, an individual might fail to detect or adequately articulate. They also might be insufficiently able to advocate for themselves despite suffering harms of it. That might be racial discrimination there. And then finally, socially, without knowledge of certain people or important cultural kind of things, so like YouTube trends or other like important memes that are important for cultural fluency, as well as like making things like small talk. So this example here is about like the ability to make small talk and how that influences your ability to get a job. This person may be excluded due to lack of relevant cultural knowledge. So the next thing what we do is we shift from fairness as it targets an outcome. And what does that mean? So group fairness, things like disparate exposure, visibility, and utility target the end user experience, but epistemic utility targets the user agency or the ability to access information. So finally, when we're shifting from fairness as it targets an outcome, what are we shifting to? So we're shifting to an equity-based universal baseline access to service. So that's a lot, so we'll just break it down a little bit. First, we provide a definition. We define infinite personalization as a system that becomes more and more personalized. There may be a point at which the estimated likelihood of being recommended some content will be effectively zero. So basically, if you have the space of all content here, over time, the system becomes more and more personalized to what you're interested in, what you have looked at in the past, what kinds of things might be your kind of like hobbies and things like that. And that eventually you will reach kind of this point of infinite personalization. And how we define this like effectively zero kind of point here is that, let me see if my slide will update. Here we go. That if you have a piece of content here, that's the red bubble, that within epsilon like additions to your search history, you won't be able to reach this red bubble. So like even if I added like epsilon numbers of queries to my history, kind of in the direction that I would be hoping to be recommended this red bubble piece of content, you wouldn't be able to reach it. So this kind of targets an unfairness that comes from a reasonable amount of effort that would be required for a user to reach their desired outcome. That's what we're seeing here with the epsilon plus one. So grounding this in the Barbie and Oppenheimer example, if you're living in a filter bubble or an echo chamber that specifically is serving you a lot of content regarding this movie because they think you have a really high value interest that aligns with the movie's values, even with epsilon additions, any kind of additions to your search query, you might not be able to be recommended something like Oppenheimer. And so of course, this is like a myopic example with something that's grounded in maybe a contextually relevant example, but obviously these can be placed with any kind of two items that are like very, very far apart or either very close to a user's interest and very far outside of them. So then with defining something that's equity-based, we define this term called, or definition of epsilon equity fairness, which is an upper bound epsilon on the number of additions to the search history in order to be recommended the relevant content. So you can see this kind of tension here with the epsilon, with the infinite fairness and this epsilon equity fairness, where within epsilon additions to your search history, then you're able to reach kind of any point in this kind of space of all content. So then with regards to equity as it targets access to information or epistemic utility, there are a couple of different candidates for targets for equity. Two of them we propose are kind of like possibilities for epistemic utility, which we kind of give arguments for why we don't do that, and then we kind of settle on this third one. So I'll give you the two that we didn't go for, which are also talked about a little bit in the paper. So the first is quality of information. This targets unfairness where one gets more utility, where one person gets more utility for their query than another. This is bad because unfortunately we don't have access to perfect information. And so that's not something we can directly control. In addition, things like targeting speed of access to information targets unfairness when one person receives the relevant information faster than another. But this disregards this idea with information specifically. It is an infinitely shareable resource. So if I were to access some piece of information first and someone else were to access it second, it doesn't change that we can both access the same amount of, get the same benefit from the information. Just because I accessed it first doesn't affect this for the other person. So then we settle on equity with respect to epistemic utility. This targets unfairness in personalized access to the information resources. If the information exists, all users should be able to access it by exerting a reasonable amount of effort. So that was the epsilon we defined before. It does not require that all queries have the same accessibility nor disambiguation, nor that all users be provided the exact same service. So that's not what we're targeting here. What we are targeting here is that we provide a soft guarantee of base level epistemic utility without grouping or comparison. If you want to hear more about this, there's more kind of like to this argument that's in the paper. So finally, what we do is we provide policies that operationalize such ideas. So what would equity look like, and how would we try to implement this? So what we do is to get everyone on the same page where people have different ideas of the motivations and responsibilities of different stakeholders and systems in socio-technical systems. So we just define these all in a table where we have government, civil society, industry, academia, and the general public. And what we do is we provide goals and then example implementations. So with each of these goals, what you can do is you can look at the implementation and decide, yeah, this makes sense. This is what it might look like. And these are what stakeholders might be involved in it. The nice takeaway here is that like most of our kind of examples require like the keynote speaker said, like buy-in from everyone in the system. And the goals still here are something where even if you don't agree with like the example implementation, you can still kind of move forward with this goal. So an example for mitigation that involve this we kind of talk about with a collaboration between industry, government, and academia. Specifically, a contribution from industry/academia might be something like developing algorithms that facilitate connections between disjoint parts of the data manifold. This might be analogous to connecting different parts of the internet together through links that are done by creating arbitrary injections that fabricate similarities or links basically between disjoint parts of the training data. So that would make that epsilon jump like more reachable. For a goal of auditing, a contribution by civil society might be reporting the utility distributions for non-users to compare against those that are already using the service. For transparency, a government contribution might be something like providing clear consequences and/or reparations for users affected throughout improvement processes and through continued negligence processes. For individual control, this might be something like where the general public can participate and provide feedback on norm setting for what features are available, how accessible services should be, determine embedded values such as degree of reasonableness, like the epsilon, the domain specificity of epsilon that we talked about before, that's feasible and realistic for users. And then finally, for education and awareness, that might be collaboration between industry, academia, government, and the general public, where they provide workshops and training sessions that facilitate comprehension of the dangers and limitations, how to better calibrate users to appropriate expectations for functionality. These workshops can include education on rights and how to advocate for them. For instance, if companies fail to comply, where people can file their grievances so that they can be collected and aggregated all together to be analyzed and reported. So in summary, we have this big green chunk here. We broke it down into a bunch of different things. We developed the inherent tension between group fairness and personalization, as it was formalized as conditioning on sensitive attributes and why that's difficult, as well as conditioning on user search history and why that's difficult. We provide a philosophical argument for fairness in terms of epistemic harms, and we shift from fairness as it targets an outcome in an equity-based universal baseline access to service in terms of infinite personalization and epsilon equity fairness. And then we provided policies to operationalize such ideas. So this concludes my presentation. Obviously, this is a workshop paper, so it's kind of open work that we're continuing to work on. And so this is one of the ways that we're kind of asking for feedback. So I'm happy to hear any of that if you're interested in helping shape where this goes in the future. Definitely there's more details in the paper, so please go read it. And thank you for your time and attention.
Hey everyone, I'm happy to be here. My name is Parnian, and I'm presenting this paper on behalf of Beauty Tech Amazon, where we are trying to improve the beauty product shopping for customers. And the title of the paper is Improving the Accuracy of Beauty Product Recommendations by Assessing Face Illumination Quality. My colleague Jenny is also here, and I'll ask her to pitch in whenever she thinks we need more explanation somewhere. So let's start by answering the question of why do we need personalized beauty product and why does this matter? So beauty product is one of those products that needs to be tailored towards specific needs, concerns, or preferences of the customers. For example, we need to know what is someone's skin concerns, skin color, hair concerns, and stuff like that before recommending beauty products. And this is being done traditionally by asking customers a series of questions, and they need to answer very specific beauty-related questions. This is oftentimes difficult for customers because they are not experts in beauty products and they're not sure how to answer. Furthermore, this is very time-consuming for them. There are existing predictive models that sometimes offer inaccurate results, and they might not resonate with the customers due to their limitations. So a fresh approach to beauty product recommendations is to leverage camera images which are taken by the user on the fly, or they have uploaded by their choice. And then we use these photos to determine facial features. And then using this facial feature, we are able to recommend beauty products that is more aligned with their needs and with their concerns. So this framework builds user trust, and furthermore, they are able to feel involved in the whole beauty shopping experience. So there is a big gap between these convenient experience for beauty product customer and the accuracy of extracting facial features through camera images. And the limitation is that poor illumination can greatly affect what we're extracting from the images. And this inconsistent lighting makes us recommend products that are sometimes worse than random. For example, we are totally getting the skin color wrong, and we are recommending a beauty product such as foundation or concealer that is not meant for that specific skin color. So what we propose here is to have an automatic model that can inform users in real time about their lighting situations, and they have the opportunity to change the lighting conditions and capture a better photo. And of course, they are always given the option to just upload whatever photo they want, and they will know interactively that this may not be the best recommendation for them. So you can see an example here. This photo on the middle is a person under good illumination, and we are showing on bottom the skin color that we were able to extract from this good illuminated photo. And then these are, for example, the concealer or the foundation shades that we are recommending for this specific skin color. And then on the left and on the right, you can see the same person under illumination that made us recommend products that are not meant for skin color, for this specific skin color. So we need an illumination assessment model that can inform the user when there is bad illumination. But the current illumination assessment models are not good enough, and this is a less explored avenue. So the limitations are most of the existing models are dependent on reference images, or they require special requirements from the customers. For example, they need to hold a color calibration card, which is not very realistic and optimal for customers. Most of the models are very simplistic. They might be trying to model pixel level quality rather than image level. And then the biggest gap here, the biggest gap here is dataset diversity, which means the dataset used to train these models are often biased toward light-skinned people. And what happens is that when they are fed with someone with dark skin tone, most of the times they just classify those as a bad illuminated photo, which is definitely a bad experience for beauty customers. And then even with a good data set, in terms of diversity, there is still an open challenge in machine learning to effectively disentangle illumination and skin tone. So what we proposed in this study has two parts. The first part is dedicated to only generating a diverse data set that includes a diverse illumination patterns, and then this data set is used to train a CNN model to output bad or good illumination. So the data creation in general is composed of first generating synthetic skin tone models, and then using a face data set, a real face data set that is not diverse, which means in our case, it only includes light skin faces. We transfer these skin tones to this face data set through a histogram matching technique, and we come up with a face data set that is more diverse. Then since data set is captured in neutral lighting, we still need to apply different illumination patterns on top of that. And for this, we again synthetically generated different illumination patterns for different skin tones. And then we use a deep learning model for light transfer, which means we transferred illumination patterns to this diverse face data set that we created. And then this whole data set is then fed to the CNN for the problem of illumination assessment. So let's look at synthetic data generation in more details. So first, to create light and dark skin tones, we use a 3D modeling software. So on the right, you can see a light skin and a dark skin model that is synthetically generated. Then on top of these skin tone models, we developed 200 distinct illumination patterns that we labeled as good or bad for the upstream task of beauty product recommendation. To apply these illumination patterns, we have utilized 2 spotlight sources in these 3D modeling softwares. And these spotlight sources are moved along the grid relative to the human model to come up with really diverse illumination patterns. And then histogram matching is used to transfer skin tone, and a deep learning model called Deep Single Image Portrait Relighting, or DPR in short, is used to transfer these light patterns to the generated face data set. So if people are interested in this DPR model, you can see it in this figure here. So this model is developed by some Amazonian authors, but it's now publicly available. So in short, what this model does is to take a face image as input, which is then fed through some encoder layers to first predict the lighting condition on top of the input image, then having it so then having this input image and the target lighting condition, we can come up with an output image from the same person, but having the target lighting. So for example, in this figure, we were aiming for a face that has this dark shadow on the right. And as you can see in the output image, the same person has that dark shadow on the right of her face. So we also had to omit irrelevant background information from the face photo, which we do using a solution called MediaPipe, which is developed by Google. And then the constructed data set is fed to MobileNet V2, which we chose for this specific task because the architecture can be run efficiently on edge devices such as mobile. And we also gave more weight to good illuminated faces because they were the minority class, and we need to handle class imbalance in this case. So moving on to the main task of beauty product recommendation, we developed a framework which consists of a color extraction phase, which can be used for both face photos and product images. So what this framework does is to first get an input image, then it goes through a background removal phase, and then having a color information. For example, given foundation products, we have an estimate of the color range that these foundation products that can have, and then having this color range, we can do clustering or segmentation on top of images. Then we do color selection by basically choosing the biggest cluster. And then the outcome is the representative color of that product or that face. So in the middle, you can see an example workflow for first the product and second for a face photo. And both output the color for the product or for the face. So in summary, for the color extraction framework, We utilize this for both product and face images. Process involves background removal, color extraction in a fixed range, k-means clustering for prominent color identification. And then for this specific study, we extracted about 2,000 foundation shades to experiment and to see how this illumination model is affecting the final result. And then we had to match the color extracted from the product to color extracted from people's face to recommend them a product that best matches their needs. And for that, we used a distance metric called CIEDE 2000. So we start our experiments by first seeing how the illumination assessment is working and how accurate is the illumination assessment model. So we compare this model with first a model developed by authors called Zhang et al. So they basically do the same thing. They are also using synthetic data, but the difference is that in their framework, the data set is not diverse. They are only including light-skinned people, which means basically their model will classify all dark-skinned people as bad illuminated. And we also compared our proposed model with the same model that is trained on light-skinned people only. And then we show here that in terms of accuracy and sensitivity, our model is definitely doing better. Specificity is higher for the model developed by Zhang et al. And for the light skin model, and that's only because they are basically classifying all dark skinned people as bad illuminated. And then on the other hand, they have low accuracy and sensitivity. So this is a demo of my own face under good and bad illumination. So the model here is supposed to classify each frame of the video as good or bad illuminated. So as you can see, it starts off with good illuminated, and then it goes to bad when there is this shadow on the right side of my face. So it is still bad. It doesn't show the skin color or the skin concern or other facial features accurately. And then in the end, we again get some good frames. So we are basically asking the users the same thing. We want them to, for example, change the room or rotate a bit to get a good illuminated photo before they see the recommended beauty products. So this is the experiment. So for the color extracted on as only less all this are like 3 more examples. The first year first and illuminated built any but then if you had that comment, but there are also some extra shades that are not accurate. We can also see comment shades that if we comment to the user and to the user. So we gonna share about the image and this beauty product is not its customer is aimed to increase customer taking account and our experiment so that our proposal is outperform and then needing for responsibility for the final classification and other count string tasks. Can
Okay, I'm Giacomo Medda from University of Cagliari, and we present our work regarding consumer unfairness mitigation and counterfactual graph augmentation recommendation. I would say in recent years, there's been increment of works regarding explainability and fairness recommendation, also due to recent regulation like the European Act, but also due to several surveys that highlighted how most of the works only aim to improve explainability, only mitigate unfairness. Indeed, there are just few works that analyze the interrelationship between them, and there was just an attempt to inform mitigation procedure with explanation techniques, and was not done in recommendation. Our contribution is an algorithm to mitigate unfairness, consumer unfairness recommendation, and this algorithm leverages and extends explanation techniques usually adopted for graph neural networks. We will say this algorithm augment graphs in order to make the recommendation list, the resulting from using the augmented graph, favor across demographic groups of consumers. I just describe briefly the recommendation task based on graph, where generally we can, I'll say, encode users and items as nodes, and the recommendation task is a linking prediction task. So we try to predict the probability of a link between a user and an item. And usually the graph is represented as an adjacency matrix where the entries equal to 0 mean there are no interaction, while the other means there are interaction between a user or item. A classic graph neural network takes in inputs the adjacency matrix and returns the probabilities of the linking prediction across all the user and items links. The mitigation task is represented by the fairness loss here below, and you can see the augmented graph, which is highlighted by the tilde over it. And there are two losses: a fairness loss, which optimizes for the consumer fairness, and the distance loss, which tries to minimize the augmentation graph. The augmentation, or I say algorithm, is composed of three components, where the first one is the augmentation mechanism that leverages a perturbation vector to add the edges, as noted by the green arrows on the chart. Its goal is to update the values in the augmented graph depending on the corresponding entry. In the optimization process, however, we need to use its approximative version. So Usually the perturbation vector is only zeros and ones, while in the optimization process, we use a real value one, which then, once ready, we'll apply a sigmoid step and a binarization step to get the final one of 0 ones. The second component is the augmented graph generation component itself, where this is an iterative process. So we start from the original density matrix. Then at each step, what we done is perturb the graph with a perturbation augmentation vector to generate a new augmented graph. We feed this augmented graph to the GNN, retrieve the linking probabilities, which have been altered, and we estimate again the fairness on this new recommendation. And depending on the value of the consumer fairness loss, we update the perturbation vector to add the new edges or not. Almost say the iteration stops until a condition is met, or maybe like we need to continue, so it goes to the next iteration. The last component is the fairness loss itself, which is composed of two terms. The first one is based on demographic parity, so we can operationalize as other works like as the absolute difference in recommendation utility across demographic groups. We choose to use NDCG as recommendation utility, but only on the evolution phase. While during the optimization, we use an approximative version, which is like depicted here. And you can check our paper to know more details about this function. The distance loss merely checks if how many changes there are between the augmented graph and the original one. So we apply a sigmoid to bound the loss to the same range of the fairness loss, and use a factor to to decide the importance of the minimization of the number of edges added to the graph. We'll say, how do we measure the NDCG during optimization? We cannot use the relevant adjustments of the evaluation set, obviously, otherwise it wouldn't be a mitigation set. It wouldn't be a mitigation. And we use another set. We call it perturbation set, which can be validation training. We use the validation set one. And we need also to denote that we work on a binary settings. So we just do demographic groups. And we denote the advantage one will be with a higher utility, and the disadvantage one is the group that experience lower utility on the perturbation set. Given that our goal is to mitigate unfairness, we aim to increase the utility of the disadvantaged group, and not so I would say decreasing the advantage one. To this end, we only augment the disadvantaged group. So we only add edges to the user nodes of the disadvantaged group. Anyway, nonetheless, we still have so many edges that we can add, and so the dimensionality is too big. And we need to consider some sampling policies to reduce the set of users to add edges or the set of items. To do so, we have the base sampling policy, which is we had all the edges. The zero NDCG, where all the edges are only added to the disadvantaged user nodes that experience NDCG equals 0 on the perturbation set. Then we have the low degree ones, where we add edges only to the user nodes that have a lower degree, the lowest degree, so have fewer interaction compared to the others. Sparse, which adds edges only to the user nodes that mostly interact with each items. And then we have the farthest, which add edges only to the user nodes that are the farthest from the advantage ones. And we have the item preference, where we add only interaction with, say, items that are mostly preferred by the disadvantaged group. Like, for instance, we could say, just for example, we say that maybe all the consumers prefer Western movies. So we point to the Western movies to reduce the space. So they are based on some kind of, I would say, heuristics. And we also contemplate the combination of IP with the other policies, since I would say they affect different sets. For our experiments, we use the data sets, movie less 1M less than 1K, where there is the group's representation is denoted here as F, where F is females, M males, Y younger or older. And we split each user interaction with a ratio of 7:1 in order of recency and using, as said, the validation as perturbation set. We adopt three models, free GNN-based recommended system here. And to start with experiments, the first thing we have done is see if the augmented graph has a real positive impact on consumer fairness, specifically on the perturbation set, which is the one that we use in optimization. So the fairness loss can be denoted as the different disparity in DCG. And we first consider the delta DCG before the augmentation and after. We can take the relative difference between these two values. So we denote a negative value as positive for us, a positive impact, because it means the disparity decreased. So we got a mitigation. So we first focus on movement 1M, where the highlighted values denote a mitigation. And we can see there are several experiments that work. Especially one of the things I want to highlight is how important were the policies, because you can see there in these two columns, only one of the policies was effective. So it means that reducing the set of users and items is important and is a policy that needs to be accounted to get effective results. We can also see that this policy is the most effective one that doesn't work for just one of the settings. And NGCF proved to be one of the most robust models that we used. So it did not get affected by the added edges mostly. Then we have last F1K, where we see more mitigation comparing the values. Especially we have more policies that perform better on all the settings. And we also see that still NGCF is a robust model. So in this setting, I will say only for gender, it's hard to get an impact to adding edges to the graph. The second experiment we wanted to do is a comparison with other works that have been, existing work to mitigate consumer fairness recommendation that we reproduced in our preview works, if you want to check. And they were devised for, top-end recommendation as our work. We compared these works in this chart, where you can notice that this is a chart to note the trade-off. So on the y-axis, you see the relative difference in delta and DCG. So it means that points that are below the origin are mitigation. So the disparity was decreased. Otherwise, on the other part, like in the x-axis, we have the relative difference and DCG, which means that points at the right of the origins are increment in utility. You can see that our approach, which is denoted by the red stars, is systematically below the origin, but also is often at the right of the origin, which means that it mitigated unfairness, but it also increased the overall utility. And to show also the performance of our method, we also took the values after each algorithm was applied. And we can see that our method in particular has the best and second best values, where the best values is highlighted by the bold and by bold values, and italic for the second best. And we can see that this graph-based recommender system are useful, reliable, and to be effective to get fair and util recommendation for the users. So as a conclusion, I would say that we have shown that our method is more reliable compared to other state-of-the-art algorithms. And also, sorry.
All right, thank the speaker.
Okay. Oh, yeah, I heard something. I thought we were speaking.
I thought you were done. I'm sorry. The audio cut out.
Okay. Well, no, we've seen that we reduce the added users that receive no relevance. So we have the zero and DCG group positively affects the utility, and the future work will consider new policies, also objective function like personalization. So thanks for your attention, and if you have any questions, please, and also if you want to participate further.
Okay, hello everyone. My name is Mohamed Mehdi, and I'm excited to share with you our research on provider fairness and beyond accuracy trade-offs in recommender systems with my co-authors Saida, Hussein, and Leila. Recommender systems have become an essential part of our digital life, and they're often the reason we find that perfect movie to watch or the item to buy. However, recommender systems are suffering from popularity bias phenomenon. Popularity bias refers to the phenomenon in which popular items are disproportionately recommended over the less known long tail items. So this will put providers offering the niche items in a great disadvantage and causing unfairness for the providers. On the other hand, popularity bias impact the users as well, as it may limit the diversity of recommendation that we get and reducing the likelihood of being able to discover something new and unexpected in the catalog of the items available. So in other words, it may adversely affect the quality of recommendation beyond accuracy, including the diversity, novelty, serendipity of the recommendation. So popularity bias, without doubt, is a problem that needs to be dealt with. In the prior research, the focus has been primarily on addressing popularity bias in recommender system, but with the focus on improving the overall accuracy of the recommender system by addressing the popularity bias. While this is undoubtedly important, it tends to overlook some critical elements that exist in the system, such as the fairness to the content providers or the effect that it might have on the beyond accuracy metrics. So our goal in this study is to rigorously examine the trade-offs that are involved when we take measures to address popularity bias. So once we have improved the exposure of long-tail items, the question would be whether are we improving the recommender system quality as a whole, or there are some trade-offs in the process of dealing with the popularity bias. To do this, we started by introducing a simple yet effective algorithm to address popularity bias that is inspired by the prior works in post-processing techniques. Post-processing techniques has shown to be effective in improving the objective function of the recommender system without taking a considerable toll in the accuracy. So the post-processing models are quite versatile in the sense that they can be applied on top of various baseline recommendation models. And this is particularly significant for real-world application, where a lot of work has already been done in designing a custom recommendation algorithm, and now they're trying to address a particular problem like popularity bias on top of their base models. So next, we will use this model to address the popularity bias and try to study its broader implications on various evaluation metrics in the recommender system, such as its potential trade-off with provider fairness and beyond accuracy metrics. We have evaluated our work on 4 baseline recommendation algorithms and 4 dataset domain in order to minimize the impact of potential randomness in our study. All right, so now that we discussed the problem statement and the goals, let us dive into describing the algorithmic model that is developed and has been used in this paper. So our approach essentially begins with dividing items into 2 categories, those that are popular and those that are not popular. So variable yj here in this slide is a binary variable that the value of 1 shows when the value is 1 when the item belongs to the popular group and 0 otherwise. So we use this classification variable to define a fairness metric, which we notate here as f. It's it's shown on top of this slide. So this metric captures the difference in exposure between popular and non-popular items in the recommended list of items. So when the value of f goes close to 0, it indicates that both groups of items are getting equal attention in the recommendation list, which is the optimal goal in achieving provider fairness. So we have employed an integer programming model to mathematically define this metric f and design the algorithm to re-rank an initial list of recommended items that is provided by that baseline algorithm. So this initial list is generated by a baseline model. For example, a matrix factorization model suggests that a list of recommendation. We get the list of recommendation and feed it as the input to this re-ranking algorithm. And X would be our binary decision matrix in which each of the elements of X, the Xij, gets a value of 1 when the item J is recommended to user I and otherwise 0. So our objective function here is to recommend items in a way that it maximizes the summation of overall scores, while it's also being penalized by the deviation from provider fairness. So the objective function is defined here in line 5. You can see the first part of objective function, the Rij multiplied by Xij, shows basically the summation of scores we get from the baseline algorithms, while we are penalizing it with the F metric that is defined here. In terms of constraint, the constraint of the model is that first of all, the variable Xij has to be they all have to be binary, making it a mixed integer programming. So either the item can be included or not included in the re-ranked recommendation list. Furthermore, exactly k items should get recommended to each user. So to address the top k recommendation problem. This problem is not trivial, and it's actually an NP-hard problem, meaning that getting a global optimal solution is very challenging. But there exist many heuristic methods and solvers that can be used in practice to provide us with good solution that can be used in practice that satisfies the constraints. One other things to mention before moving on to details of the result is that the importance of the hyperparameters lambda here in the objective function. So the high value of lambda can put high emphasis on the fairness metrics. However, it might sacrifice the accuracy aspect of the recommendation system. And having very small value of lambda will give all the focus to the recommendation accuracy. So it's very important here to carefully tune this parameter. And in our experiment, we also provided a very thorough grid search in order to tune this parameter to achieve a balance between the provider fairness and the and trade-offs between the accuracy metrics. So in these slides, you can see the statistics of the datasets that has been used in our study. So we have used 4 datasets from 4 different domains, including opinions, book crossing, Guala, and Last.fm dataset. And Last.fm dataset. And for the baseline recommendation models, we have used Poisson factorization, weighted matrix factorization, neural matrix factorization, and the variational autoencoder collaborative filtering model, which are the most commonly baseline models that has been used in fairness analysis paper. And that's why we adopted these same baselines to provide a comparable analysis. And for the evaluation metrics, as you can see, a diverse set of evaluation metrics has been chosen, ranging from precision recall, NDCG, diversity, novelty, coverage, serendipity, personalization, and item exposure. All right, so let us now dive into the result. So here you can see the results for all baseline models before and after applying the re-ranking algorithm to treat popularity bias. N values in the type column represent the neutral baseline models, and the P represent the model that the re-ranking model that has been proposed in this paper. As we may see, the re-ranking algorithm has been able to create a much more equitable distribution of exposure between long tail and short-head items. So this can be seen from the column group of item exposures on the right side of this table. For example, in the Poisson factorization baseline and opinion dataset, which would be the first and second row of this table, we can see a change from having around 22,000 short-head items being exposed in the recommendation list to only 8,300 short-tail items. And on the other hand, increasing the exposure of long-head items significantly from 4,000 to 18,000. But the important thing to notice here is that the number of relevant short-head item and relevant long-tail items has remained relatively the same. So even though the algorithm has recommended much less number of popular or short-head items, we can see that the number of relevant short-head items is very close to the original baseline models. While on the other hand, for the number of relevant long-tail items, we have seen a considerable increase from 3,000 to 600, from up to 4,700 approximately. So in this graph, we provide a high-level view of our previous result paper, capturing the performance on overall data set. Each box plot represents the measured performance for a specific evaluation metrics over all the experiments that we have. So in graph A to C, we have seen that we see the metrics related to the accuracy models. So as can be seen, there exists a slight trade-off when we have achieved provider fairness in the recommender system in terms of accuracy metrics. But the amount of this slight trade-off is different between different baseline models. Some of them are performing better, while others are suffering more from this trade-off. While on the other hand, for the beyond accuracy metrics, we have seen improvement across all of the metrics in the graph D to H. Surprisingly, for the personalization metric, we have seen the least amount of improvement, and that essentially shows that while we are succeeding in making the list of recommendation more diverse, we are not necessarily getting better at matching these diverse items to the user who would most appreciate them. So there is a lot of room to improve the work on matching the users who are actually interested in diverse items with more diverse sets of items, rather than simply increasing the diversity as the current models tries to achieve. So to conclude, we have introduced a fairness FR re-ranking algorithm that has been aimed at mitigating popularity bias. We have employed a comprehensive evaluation metrics using different beyond accuracy metrics that has been used, like novelty, diversity, coverage, and serendipity. We analyzed the trade-offs between fairness for providers and other recommendation quality metrics. And our findings shows only a minor reduction in recommendation accuracy and overall improvement in all beyond accuracy metrics, indicating that fairness can be actually achieved without significant compromise to the system's overall effectiveness. Finally, we have made our codes and datasets open source, so you can run the experiments and reproduce the result. Thank you. If there is any question, I would be happy to address.
So my name is Ashmi, and I'm a PhD student at the Technical University of Munich. And today I'm going to present to you our paper on so basically it's a literature review that we conducted on the understanding the individual and multi-stakeholder fairness in tourism recommender systems. And the original work, or the long version of the paper, was accepted in the Frontiers Big Data Journal. So if you want to take a look at it, please feel free to do so. And this is a joint work together with Paramita Bonik and Wolf and Londo, also from the team unit. So we are planning to cover the following today. So first, I'll give you an introduction of a little bit about tourism recommended systems and what the stakeholders are involved in this whole process, and a little bit of the basically laying the ground for this. Followed by sharing the findings from our literature review with you. And last but not the least, we will hopefully have some time for Q&A and discussion. So the stakeholders in tourism recommended systems. So first of all, I guess most of you in this room are acquainted with what tourism recommended systems are. So anything that helps you with trip planning or hotel reservation, restaurant recommendation, anything that is a part of this whole touristic life cycle is referred to as a tourism recommended system. And like any other recommended system, it is also a multi-stakeholder environment, which involves multiple stakeholders. So the first stakeholders are the consumers. So this can be the tourists, the business travelers, airline passengers, anyone who is trying to consume the service provided. Next are the platforms, which could be the hotel platforms, the e-commerce sites, flight booking platforms, etc. So yeah, and third, we have the item providers, which can be, the hotels, the resorts, the rentals, restaurants, everyone who hosts their services on these platforms. So, for example, the different hotel chains, and you have Mobile One or Marriott or so on. And last but not the least, we have identified, research has identified another fourth category, referring to the society, which involves the local environment, city authorities, municipal councils, etc., which are basically the non-participating stakeholders of recommendation. But all these people, all these stakeholders have some sometimes hidden, sometimes not so hidden agenda in this whole process of recommendation. So, for example, the consumers are interested in matching preferences, while the platforms are always interested in maximizing their commissions that they get from this recommending the places, while the item providers are always concerned about their maximum exposure that they can get by when their items are being recommended on these platforms. And last but not the least, society is concerned about environmental damage. So obviously, if the recommendation process is not sustainable or causes environmental damage, that's not okay, or that's not a good recommendation with regards to society. And therefore, as I mentioned, that recommended systems is also a multi-stakeholder environment, which involves involves all four stakeholders. And in an ideal scenario, we would expect all the four stakeholders to be equally compensated or equally balanced, or their needs to be equally balanced in this process. So, yeah. So there we actually refer to as the consumers as the C-fairness, and then we have the item providers as the I-fairness, and platforms as the P-fairness, and society as S-fairness. I guess that's really intuitive. So the next part is about our literature review, where we surveyed about 66 papers, and we tried to identify them and try to classify it, and I'm going to talk about it. So we did a literature review. We classified the papers into two categories, either individual fairness or multi-stakeholder fairness. So individual fairness, stakeholder fairness means their focus of the paper is on either of ensuring fairness for either of the four identified groups, or in the multi-stakeholder fairness cluster, we have the papers where they focus on two or more stakeholders during their fairness assessment. And next, we will also discuss a little bit about the challenges that we faced during this process. And so let's look into the individual stakeholder fairness. So The main fairness criteria that we identified using these were like the individual or the group fairness, followed by popularity bias. And then we had position bias for the platform fairness, or the ranking thing, and societal fairness and sustainability. Unfortunately, because of time constraints, I'm unable to go into details, but you can have a look at it in our paper. So, and these are the papers surveyed. As we can see that there are, even though there is a lot of paper or a lot of work on consumer and other different types of fairness, but there's very little work on societal fairness. Next, we look into the multi-stakeholder fairness, where we see that, again, the same. There seems to be some work, especially in the consumer and item provider fairness area, but when it comes to involving society as a stakeholder, there needs to be more research done in that area. And so now coming to the challenges of the thing. So while doing that, we realized that it's really difficult to model the individual stakeholder utilities in the travel and tourism domain, because it comes with other uncertainties like the travel restrictions imposed during COVID, or the seasonalities and other changes and capacity restrictions. So modeling these things were a challenge, or like it's often a challenge. Next, we have the complexity of the inter-stakeholder relationships. So for example, the rating of your room may differ on who you are asking it. So for example, like you may have different features that appeal to you when you are rating a room when you are traveling alone versus when you're traveling with family. So when you're traveling with family, the room size matters, but when you're traveling alone, I don't think that matters as much. So these are these complicated, intricate relationships that need to be considered when you are modeling fairness concerns in the tourism domain. Next, we have the thing that the explanations are often helpful in generating recommendations that are fair, or like explaining why the thing is recommended to you because the thing is recommended to you. So in that case, we see that not a lot of research has been done in this area of having an explainable interfaces. So the UIs are not really explaining why you are being recommended something, the reason for that. And that's also a challenge in fair recommendations. Next is, the last but not the least, is that insufficient data and metrics. I think this is a challenge that is encountered by other domains such as music industry as well. And this is something that we often lack the representational data and the actual data which has the user behavior or the different other information which is important for fairness research. That also includes the fairness metrics, different fairness metrics, because the evaluation criteria that differs, and therefore, like as the fairness concerns or the definition of fairness keeps changing from domain to domain and on certain conditions, or like depends on certain criteria, so it keeps changing as well. And we did not, or there are not too many evaluation metrics for that. And another thing that our literature study also revealed was that often people are suggesting ways to recommend re-ranked lists which are fair, but then no one reports about whether the users actually like the fair lists or not. And that's something where potentially we could research in the future on the user acceptance of this list. With this, I come to the end of my presentation. I will quickly summarize what we learned here. As I discussed that we did, oh, sorry, that was my alarm for the timer that I set. Yeah, so as I said, there is limited research on involving society as a stakeholder, and so that needs to be done because society is an essential feature that needs to be incorporated into our system of recommendations. Followed by the other highlight would be the limited research on explainability and the challenges regarding data availability and representational data and metrics. So yeah, with this, I come to the end of the presentation, and thank you so much for your attention.
Oh, I'm Toshihiro Kamishima. Thanks for a kind introduction. Individual fairness is a principle of treating right cases alike, which has been acted by Aristotle. Since work formalized this principle as mapping similar individuals in an original space into similar positions in a fair space. In this talk, we formalize this principle as conditioning fairness criterion by individual. This is the outline of our talk. First, we show a brief summary of formal fairness. Then, we formalized individual fairness is compatible with that of dog et al. Finally, we extend the equality laws and substantial fairness criteria. We begin with a brief summary of formal fairness. In fairness-aware machine learning, we maintain the influence from sensitive information to objective. For this purpose, we have to satisfy a formal fairness, which is the desired condition defined by a formal relation between sensitive feature, target variable, and other variables in the model. And we define some notations. An objective variable y represents an objective of decision making. Variable y represents observed value. At y represents a predicted value. A sensitive feature S represents a socially sensitive information to ignore. All features other than a sensitive feature consist of non-sensitive feature vector X. There are two major accounts why an instance of discrimination is bad. In a harm-based account, discrimination makes the discriminated worse one. In this disrespect-based account, discrimination involves disrespect of the discriminated, and it's morally objectionable. A harm-based account relates to the means utilitarianism, and disrespect-based account relates to Kantian deontology. Techniques of fairness-aware machine learning based on the harm-based account. This is mainly due to these judgments. Further, a harm-based account requests a baseline for determining whether discriminants have been made worse. Assumption-based fairness uses an ideal outcome as a baseline, and counterfactual fairness uses counterfactuals. Next, we show our individual fairness is its compatibility. Individual fairness is the principle of treating right cases alike. Could you tell me the time? Okay. We formalize individual fairness as conditioning a fairness criteria by X. For example, statistical parity independence between Y hat and S is conditioned by X, and we got conditional independence between Y hat and S given X. The formalization is compatible with the one proposed by the work. We will explain that formalization is compatible. We explain the work's original formalization. First, similar original data are mapped to similar fair representations. Then predictors make similar predictions for similar representations. In this formulation, there is no sensitive information in fair representation. This implies that the predictions satisfy fairness to unawareness condition. Fairness to unawareness is prohibiting to access individuals' sensitive information during the process of learning and inference. This means that a predictive model of Y hat given X and S is replaced with the model Y hat given X. This raises the conditional independence between Y hat and S given X. Fortunately, our re-formalized individual fairness is consistent with fairness through unawareness. From the fact, Dorf's individual fairness is also compatible with fairness through unawareness. Our formulation is compatible with that of the work. We then apply our formalization to equivalent odds and sufficiency. There are two types of fairness criteria in errors of prediction to mitigate an inductive bias, equivalent odds and sufficiency. The probability pointed out the Recsys score. The compass does not satisfy equivalent odds. The Uniscode refuted that the score is designed to satisfy sufficiency condition. Conditioning by X can convert equivalent odds and sufficiency to integral versions of them. In this criteria, the phrase tweeting arrived meaning predicting similar error rate. By adding our new criteria, formal association-based fairness can be summarized as in this figure. And conclusion is as follows. That's all I have to say. Thank you.
Hi everyone. So I'll be presenting. We're using social choice for improving fairness in recommender system. There's a lot of authors on this paper. We're from University of Colorado. Nicholas is from Tulane, and then Elena is from Bratislava. So what this paper is about, the motivation is that fairness concerns are complex and oftentimes there's multiple that we need to combine. Just one fairness concern isn't always a realistic case. So we need a way to combine these fairness concerns and balance them. So the main idea of the paper is that we are using social choice to represent these fairness concerns. And we then evaluated that on synthetic and real world data. A quick overview of what I'm going to talk about with you. First, I'm just going to give a quick introduction to what social choice is. Then I will go into a description of the experiments we did, talk about our research questions, go into data and experiment details. Then we'll talk about some results and future work. So what is social choice? Social choice aims to answer the question, how do we combine individual preferences to make a collective decision? So examples of this would be, how do we vote on a candidate, or how do we have fair division of resources? And thinking about kind of where social choice fits, what we're using is computational social choice, kind of following in with the game theory and algorithmic economics there. So the basic idea of how our experiments work was fairness concerns for a recommender system were identified, and those fairness concerns were assigned to agents. When a user arrives with recommendations, agents are allocated for that user, and social choice rules are used to combine agent votes and produce re-ranked recommendations. Why is this a good idea? You can have many fairness concerns as you want, within reason. The system is going to be dynamic, so fairness concerns are acted on when they need to be, and systems can act on opportunities to pursue fairness goals. So if there's a bunch of users that might be more beneficial to pursuing a fairness goal, those users can be more acted on. And you can draw on an extensive history of computational social choice, including provable properties, as social choice has been built out. So as a diagram, this is kind of what that looks like. We have the user, and they come in with their recommender system, and at the same time, we have the agents that are assigned to fairness concerns that we might have. That's going to go into our allocation mechanism. And then the allocation mechanism, we're going to allocate the agents, and based on those agents and the initial recommendations, the choice mechanism is going to be used to vote to create the final recommendations. So this is what the allocation part looks like. The user profile goes in, and then each of these here represent agents, and that goes a fairness score and a compatibility score from the choice history is used to determine how the agents get allocated. And this is the social choice aspect. We have those agents already allocated with the computed recommendations and the agents. The agents are all going to cast a ballot that's going to be combined into creating the final recommendation. And then that is going to go further into the choice history, which is going to be used in allocating the next agents for the next user that arrives in the system. So our research questions, first we had, do different mechanisms offer different fairness and accuracy trade-offs for different conditions? And if so, why? Do different social choice mechanisms have different dynamic characteristics? And what is the interaction between the mechanisms and allocation, and what makes for good synergy? So I'm going to go into the different allocation mechanisms that we use first, and then I'll talk about the different social choice mechanisms that we had. The first one is least fair. That's the fairness agent with the lowest fairness score. That agent is the one that's allocated. Lottery will select a single agent using a lottery that's based on the product of unfairness and squared compatibility. And weighted, all agents are allocated, but the resulting weight for the agents is based on that same product of unfairness and squared compatibility. And a note about least fair, it's going to ignore compatibility completely. So what we would expect to see with least fair is the accuracy to drop more, as fairness will be a higher priority. The social choice rules that we used were, these are the two score-based ones. We used rescoring and Borda. In rescoring, each agent, including the recommender system, contributes a weighted score for each ballot, and these scores are then summed to determine the ranks of the items.
And in Borda, each agent submits a ranked scored ballot, but the scores are ignored. The ranks across the ballots are summed, and the result determines the final ranking. For pairwise social choice rules, we use Copeland and ranked pairs. Copeland computes a preference graph over all the ballots, then calculates a win-loss record for each item, considering all pairwise comparisons. And ranked pairs work similarly to Copeland. It uses the same graph, but it orders the results by how much an item wins by. The first data set we looked at was using real-world data. It's a microlending 2017 data set with 2,600 items, 4,000 lenders, and then 110,000 ratings. We identified two protected features in this data set. Loan size. Large loans were the protected feature here, and countries with low funding rates. And then these recommendations were generated through bias matrix factorization. It's an important note that any base recommender could be used here, but bias matrix was chosen because of known issues with popularity bias. So we wanted to see how this approach to fairness could mitigate that problem. We also looked at synthetic data. Here we had 500 users and 5,000 items, and then both of these had two protected features and 200 sample ratings were generated using matrices of latent factors, and the top 50 of those for each user was chosen as their recommendation list. Then we wanted to look at a dynamic synthetic output. So here we had 1,500 users, and we put these users into groups to see how SCRUF would respond to users of different compatibility with different agents arriving at certain times. So the first group of users was highly compatible with agent 1, but then the second group of users were highly compatible with agent 2, and then the last group of users were kind of somewhere in the middle. So what goes into this? The fairness and the compatibility scores. For fairness, in our experiments, we looked at proportional fairness. The fairness scores after each user. So average fairness scores were normalized based on the performance of all agents. And the average fairness score is what we used in our results, but the proportional fairness and scores based on the agent definition is what the next agent allocation saw and what went into the history. Then compatibility was based on the entropy of users' profiles relative to the protected feature. And compatibility and fairness are input given to agent allocation. This was over 100 interaction history window. And when evaluating the results, we consider the full set of interactions, not just the window that the agent sees at each point. So for our experiments, we used these three different data sets with the three agent allocation mechanisms and the 4 social choice mechanisms. And these are the results of those experiments. So first, we wanted to look at just what that trade-off is between accuracy and fairness. So we have our NDCG to represent accuracy and the average fairness score, which was normalized fairness between both agents. And we can see that there is a little bit of, there is a Pareto frontier curve here where some different choice and allocation mechanisms are below it, and some succeed a lot more. We also see a lot of grouping between the choice mechanisms. So the colors represent the choice mechanisms, and then the shape of the points represent the allocation mechanism. The choice mechanism seems to have the most impact on kind of where the points fell on the graph, with the exception of the weighted allocation mechanism. For the weighted allocation mechanism, we saw that they were much lower in fairness and higher in accuracy than the rest of the experiments here. And lastly, for the dynamic experiment, we see a lot of changes in kind of what the graph looked like. So by changing the order that the users arrived, there was changes in how the different choice and allocation mechanisms performed. So to summarize those results, we did get clear groupings of choice mechanisms. While both data sets had different orders for which choice mechanisms worked best, we saw that for the synthetic data, ranked pairs and rescoring had kind of saved the most accuracy while not necessarily providing as much for the fairness. And then Borda and Copeland did a lot more for the fairness, but dropped accuracy further. And then for the micro-lending data, we saw that the rescoring held higher on fairness, while ranked pairs fell a lot lower for the fairness, along with Copeland. We also saw the weighted allocation in ranked pairs with ranked pairs and Copeland lacked synergy. So this was the allocation where agents were given specific weights along with the choice mechanisms that were pairwise. So these pairwise choice mechanisms are used tiebreakers, and the tiebreakers are just going to be random if scores are going to be the same. So this is one thing that we're still looking at. If we were to have a data set where a lot of items might be scored 3, all those ties are going to be broken randomly. So some way of cascading that so that ties are not broken randomly is something that we're working on right now. And we also saw that there are changes when the experiments are dynamic. So do different mechanisms offer different fairness and accuracy trade-offs for different conditions? Yes, and we can see which choice mechanisms and which allocation mechanisms do tend to improve fairness more or keep accuracy while improving fairness, but it did vary based on the data that we used. Do different social choice mechanisms have different dynamic characteristics? We saw that they do, and we're still exploring that a little bit more. What is the interaction between the mechanisms for allocation and choice, and what makes for good synergy? We saw that there are certain allocation and choice mechanisms that follow a pattern. However, for that weighted allocation with the pairwise choice mechanisms, it didn't do as much for fairness. So there's a lot more that we're working on here. One of the first things that we're exploring is what happens when we change the history window size. How much of a past should it be going into deciding what agents we should be using? So we look at just the past 10 users, the past 100, the past 1,000, and would there be a way of some sort of exponential decay for making the older users less relevant and the new users more relevant? We're also looking at hyperparameter tuning. So looking at what the recommender weight should be, and the relative agent influence, how strong of an impact should those agents have, and tie breaking for those pairwise social choice methods. If we add more of a cascade preference, where scores won't all be the same, but they'll be slightly varied, is that going to improve the performance of the pairwise social choice mechanisms? And some future work, we want to look at adding more than just 2 fairness definitions in agents. Up to no more than 10 would probably be a reasonable expectation for an organization to use, but we do want to explore more than having just 2. We also want to go beyond a single fairness definition. For these experiments, we only looked at proportional provider side fairness, but within this architecture, it would be possible to include a lot more, and there might be consumer side fairness metrics that we want to look at. along with provider side metrics that might be concerned with maybe how many items are in the top K. And we also want to look at more with balancing fairness and accuracy. Currently, the parameter that balances between fairness and accuracy is just represented by recommender weight. So we want to look more at that. And that is all. Thank you. And any questions?
Thank you, Alpha. Yeah, so I'll be presenting our work on measuring fairness in grid layouts. So there's been a lot of work on fair recommendations, and most of this work has considered a setting about like this, where you get a list of recommendations. And this particular list is from Vicky Boykis's Library project, which is a recommender system for books where you can search for books based on vague vibes. So just type in some super vague vibey keywords, and it uses a language model to find books that are theoretically aligned with that. So I asked it for tedious fantasy, and this is what it came up with. But we've got this question of like, is this fair? And there's been a lot of work on this kind of a problem. Almafa and I had a paper at SCRUF last year that surveyed a number of those metrics. Mike Kozaliki and colleagues have a paper in Computing Surveys that look at it from a different perspective, also a number of these metrics, but we've got a ranking of items and we can ask if it's fair or not. We can do that in a bunch of ways. We can look at the distribution of the exposure that each of these items receive. So I search for a rabbit and I get, and then we have this list, and because humans know about things pretty fast, the exposure value of each of these positions decays relatively quickly. And we can ask things like, are the recommendations, does a recommended item, say this, the picture of the rabbit, does it get exposure commensurate with its relevance or with its utility to the user's information needs? And you get situations like, maybe there are a number of items of comparable relevance, only one of them can get that coveted first position. And so we can ask, over one ranking or over a sequence of rankings, are the items getting exposure commensurate to their utility? This has been studied. There's a lot of interesting metrics. There's a lot more work to do in this problem setting, but there's a lot of work on this. And I go over to Goodreads, and you can get on Goodreads of recommendations as a list, but there's many, many recommendation interfaces that aren't a vertical ranked list. In Goodreads, I can see a horizontal ranked list, or several of them. I can see a grid. And grids are particularly common in media consumption, or in streaming services. Most streaming video services use a grid-based model. Netflix has done it for years, but Apple Video, Amazon Prime, most of these streaming services use a grid-based layout for showing the recommendation results. So the question is that fair? And there has been, to a first approximation, zero work on this question. When we go beyond that linear ranked list, and we want to look at these other kinds of layouts that are very commonly used in a lot of systems that millions or more people use every day, are the results fair? And we really, there's not been much work on that question. How do we even measure that? So, as I said, prior work has mostly worked on lists, not grids, but a number of the metrics are modular and incorporate a browsing model that computes a weight for each of the positions in the ranking. So those metrics seem amenable to grids if we can swap out that ranking-based browsing model for a grid-based browsing model. So that's one of the advantages of modular metrics, is you can kind of take them apart. You can replace the individual pieces as you need to for a different problem. So that's what we did in this paper. The key question that we pursued here is,
what happens when we replace that linear browsing model with a grid-based browsing model to start to try to measure fairness on the grid layout. And so to pursue that, a few things I'm going to talk about today. I'm going to give a little bit of a background on metrics and layouts and browsing models. And then we looked at 3 different research questions. The first one is fairness consistent across layouts? There's some nuances to how that's a meaningful question for us to measure, which it is, but basically, if you've got it's the same ranked output from the system, or the same base recommendations, is the fairness the same depending on whether you're displaying them in the list or displaying them in the grid? Related question, if you take one of the fairness-aware recommendation methods and use it to produce a recommendation list that is fair in a list, but then you show it in a grid, is it still fair? And then the third question is, what happens when the grid layout changes? And I'm going to talk in a little bit about what kind of induce those kinds of changes. And the goal of all of this is basically to provide a starting point, to provide some first insight into what to expect if you take some of the existing kinds of fairness constructs that have been developed in the literature and try to translate them to the grid setting, and identifying some of the areas of where do we need more research in order to be able to robustly and rigorously measure fairness in grid-based layouts. So we used a couple of metrics that we identified as very promising metrics in the SIG-IR paper last year, attention-weighted ranked fairness by Piotr Stablizing and colleagues. And what it looks at is the attention or exposure for each item based on a discounted exposure model. If you go through the list, this metric does not consider relevant, so it's just looking at how much exposure each item receives, irrespective of how useful it is to the user. And then we compare that distribution of exposure, first item's getting, I don't know, half the exposure or whatever the model says, to some target distribution, maybe equality, maybe based on the population of authors of relevant documents or something like that. The second one is the expected exposure loss metric by Fernando Diaz et al. That is particularly developed in the context of FAccTRec rankers. So your ranker is not just producing a deterministic single ranking, but it's a policy distribution over rankings, and the individual rankings actually a draw from that, so you can compute expectations over rankings. And but also it accounts for relevance by computing what the exposure different items would get under an ideal policy. And typically the ideal policy is the policy that makes every item with the relevant, every ranking with the relevant stuff at the top and the irrelevant stuff at the bottom equiprobable, so that you get the relevant items get shuffled among the different ranking positions. And what it does is it compares the distribution of exposure provided by the system's actual rankings or the system's actual policy to the distribution that you would get under this ideal policy. And it sees how far apart they are, so we can assess, like, are we matching the distribution we would get under the ideal policy? So those are the metrics. Layouts. So it turns out, there's some color problems here. I didn't correct those when I copied from one slide deck to another. There are words in these arrows, but I'll talk through it. Turns out there's a variety of different kinds of layouts. So in the ranking layouts, we've got in the top left, we have the vertical list that I talked about. It's still common in many different kinds of systems. We see it a fair amount in music. Another place where we see this a lot is social media platforms, where your timeline is a ranked list. But there's also ranked lists that are shown as rows instead of columns. Sometimes these are like a carousel in the middle of another ranked list, like a carousel of news stories in Google search results or something. But you can have horizontal ranked lists. That difference does matter because user attention changes. We don't have the same browsing or attention behavior going down a vertical list as we do going across a horizontal one. But then within grids, there's actually, again, two different designs we've identified here. One is the top is what we're calling a multi-list grid, where the grid is made up of rows and each row is a different recommendation list. Maybe it's from a different algorithm, maybe it's from the same system, but it's restricted, say, to a different genre. So if you're at Netflix, you'll get different rows. One will just be popular, and one will be like for you, and another one is fantasy or whatever. But each list is different. Each row is different. The other grid layout that we see is a wrapped grid, where it is one ranking, and it's just left to right, left to right, left to right. And this shows up in image search a lot, and it shows up in Goodreads grid-based recommendation. Like, there's actually two different views. Goodreads has a multi-list grid, and then when you click show all, it gives you a wrapped grid of just that list of the multi-list. So we have a variety of different layouts here. We're focused in this work on the wrapped grid, mostly because that is the one where we could find the most prior work on how user attention flows throughout it. And then we have browsing models. So a browsing model is a function that estimates the amount of attention users are going to pay to each item in different positions. And there's a variety of ones in linear ranked lists. Logarithmic is common. If you've ever computed NVCG, you probably need the logarithmic browsing model. There's probabilistic models, the cascade and the geometric models that represent a probability of looking at an item that's based on a skip probability. In geometric, that's all we consider. It's like the skip, a probability of the user going to keep going. The cascade model looks at, it bases that probability on relevance. So you go through, like you look at an item, if it's relevant with some probability, you're going to select that item and stop, so you won't see anything below it. And also with some probability, you're going to abandon the entire list, so you won't see anything below it. So those two allow us to compute probabilities of viewing an item, and that probabilistic model of the attention lets us, it gives us a browsing model that's computing probabilities, which then gives us a lot of flexibility as to how we compute those probabilities. So, and it also lets us expand, say, to think about users having probabilistic state transitions, so we can start to expand how we are computing the model. And so, yeah, there's a variety of browsing models here that we've just talked about. And for the geometric, we've got the probability of examining or visiting an item exponentially decreases with the position, and the cascade, as I said, it depends on the relevance of the item, whether or not you're going to stop at that position. When we go to grids, there's a variety of behaviors that have been studied and examined in the existing literature that show how user browsing behavior differs between lists and grids. And existing literature has demonstrated a few patterns, some of which kind of seem contradictory at first glance, but in different contexts and different layout designs, people are going to exhibit different behaviors. So one of them is F-shaped, where you focus basically on the top left, and you have more focus going down than for the right columns, and going right than in that first row than further down. So it's this top left biased behavior. There's also a central fixation tendency where you might skip the first column or two in the first row or two, and you kind of look at the middle first, or pay the most attention to the middle. There's also a phenomenon of row skipping where you may not examine every row. So in a linear ranked list, you might skip an item. In a grid, you might skip an entire row as you're looking at the grid. And then also slower decay, whereas, as I said earlier, our behavior scanning horizontally and scanning vertically is not the same. So in the slower decay model, basically, with your attention does decay as you go from left to right, but more slowly than your attention decays as you go from top to bottom. So your patient's the probability you're going to continue on to the next row is lower than the probability that you're going to continue to the next item in the same row. So with all of that, we did a little bit of scoping. We focused on wrapped grids mostly because there has been very, very little work on how user attention, at least public work, on how user attention flows in a multi-list setting. We use the two metrics I mentioned. We model row skipping and slower decay. Those are the ones where we could find from the existing literature better actual models with some parameters we could try, because our goal here was not to develop new browsing models, but to apply the existing browsing models that we could find in the prior literature to this problem. We looked at a book recommendation setting using collaborative filtering algorithms from the previous study on author gender and book recommendation. Our fairness goal was to be fair to authors of different genders. And then we used the greedy EQ re-ranker from that same paper as our fairness aware recommender for this. What happens when we take a list fair thing and translate it to a grid. So with all of that, so looking at research question 1, what we have here is we take the same ranked list and then we lay it out in a grid, or consider it laid out in a grid, a wrapped grid, and we use these different browsing models. So the red bars are when we just use the list-based browsing model and measure the fairness. The green bars are when we use a grid-aware browsing model that models row skipping. And then the blue ones are when we model slower decay. Future work is modeling both of those together. And we see a few things. So changing the layout substantially changes the fairness score. Sometimes worse, sometimes better, but it does change. And so, for example, we can see in the top left, when we're measuring AWRF, we're using a cascade model. For all of the algorithms, the system was less fair when we considered the slower decay browsing model. And since all of these are targeting the same target distribution in terms of author gender, the target distribution for these actually does not depend on the layout, because we want, say, all authors of relevant books to get the same exposure. And things are normalized to distributions, so we can't actually compare between the different browsing models. They produce comparable results, so we can't actually say, yeah, that higher value does mean it's less fair. That's a valid comparison. But also, the system ordering is not the same in all cases. So changing your different browsing model can result in a different system being the most fair. So if your goal is to produce a fair system, is this system more fair than my existing one? Well, that answer to that question could depend on your browsing model when you're going into one of these other settings. So our first takeaway here really is, if you want to robustly and accurately measure the fairness of your recommendations, you have to use a browsing model that corresponds to the setting that you're actually going to be displaying in the user setting. This does actually matter, the browsing model, when we're going to go and measure the fairness in terms of both the absolute fairness value and the relative value that's ranked in the systems. So the next question, we looked at the fairness optimized ranking. So we took our recommendation list, we ran them through this greedy EQ re-ranker to produce rankings that were fair, and then we laid them on a grid. And again, the colors mean the same things. And again, we find so that the differences though become even more pronounced. We made that list fair in the list, and it is more fair. Like if you compare the two things, say let's look at the BPR on the left, the red bar, the list. We go from the untreated one to re-rank it. Yes, that fairness value improved, but the slower decay model is not near as fair. And so we do need, not only do we need to have the model when we go to measure, but we need to have the model when we go to optimize. We need to be able to account for the actual layout and how users are going to be browsing it. So then, and I'm gonna go quickly to get to the last bits here, but layouts actually change in practice. When you go from device to device, your phone doesn't have as many columns as your laptop or your TV. Or you take your tablet and you rotate it 90 degrees, you maybe lost or gained a column. And so the layout changes. So the question, and they can change in at least in two ways. Some respond to the decreasing columns by rewrapping. Others just chop off, truncate the right-hand columns, and they could disappear. So we wanted to look at how does the fairness change as you change your layout. And so the charts are here. You can consult the paper for the details, but basically it does make a difference. And not all metric and model combinations are equally susceptible. For example, making sure you have the right truncation approach in your model or for your measurement matters more for some metric and model combinations than others. So that kind of gives you guidance of, depending on your context, what do you need to prioritize on developing the better browsing model to ensure better fairness in your platform. So takeaways for this work. Fairness is sensitive to layout. That's like the single biggest high order takeaway. Yes, this layout and the browsing model in this layout matters a lot. And so we need accurate models in order to accurately measure the fairness of the system. And making it fair on one layout, particularly making it fair on a linear layout, doesn't mean it's going to be fair in a grid. So, I'm going to take my fairness ranking, I'm going to apply it to my rankings, and then I go show them in a grid. I might have improved fairness, I might not have. We really need to target the actual layout. Not all measurement contexts or browsing contexts are equally sensitive, so you can think about some prioritization there, say if you have a particular budget for developing your models. A lot of future work to do here. One is the biggest first future work would be developing these better models of user browsing behavior and attention. Like, there's been almost nothing on multi-list grids. So if you're going to go try to measure that, the public research literature doesn't give you much to work off. So there needs to be a lot of work needed or done to understand and to build and validate models of how users distribute their attention and how their browsing behavior, like how they browse from one item to another in these kinds of grid layouts. Developing actual algorithms that can do fairness-aware grid layout rather than just fairness-aware re-ranking in a linear list. Future work as well. And then also, we've been looking at grids, but there's a whole bunch of other layouts, like voice responses are a layout. They're just not a visual one. And they're linear because you can't speak in two dimensions, but they're a very different pace than a grid. Or as VR and AR do more things, what happens when you have like a three-dimensional VR layout of recommendation results somehow? How do users browse that? So there's a lot of, as we go to different layouts, how do users browse? How does that affect our fairness? So, all that, questions?
Thank you very much, Caroline. Hello, everyone. I'm Amin Abulqasemi. I'm a PhD candidate at Leiden University and also a Marie Curie Research Fellow at European Union Industrial Project. I'm happy to present our work titled on the explainability of exposing query identification. This is a joint work with my supervisor, Susan Weber from Leiden University and Leifa Zopardi from University of Strathclyde in collaboration with Martin de Rijke from the University of Amsterdam. Exposing query identification is a task of identifying queries for which it is likely that a retrieval system shows a given document in its ranked list of retrieved documents. And prior work has defined this task as a task of retrieving a list of queries out of a query log, which will expose a given document. And these queries, as I said, are usually from a large set of query log. The performance of an exposing query identification system is evaluated using ranked exposure list quality as a two-sided metric. This metric measures the extent to which the retrieved exposing query list is the same as the ground truth exposing query list. As we can see in the equation, RELQ is a multiplicative metric which accounts for both the exposing query identification system and the document retrieval system. In the side of exposing query identification system, mu determines how a user inspects the queries in the list of retrieved exposing queries. And in the side of the document retrieval system, G, or the gain for query Q, determines is actually determined by the level of exposure the document retrieval system gives to the document D when the query queue is being issued. The task of exposing query identification is also closely related to the retrievability estimation. In retrievability estimation, the goal is to measure how likely it is that a document shows up in the top K results of a search engine. And this estimation is achieved using a large sample of queries being issued to the system and followed by measuring how frequently the document is retrieved by those queries. But the thing is that the purpose of exposing query identification mainly fits into the context of search transparency, which is achieved by making the user aware of those queries for which a given document they are about to publish, let's say a tweet, would be retrieved in the top K results of a search engine. And in fact, showing these queries to a content creator can warn them about the potentially sensitive content being issued by, could be issued by the search engine. Exposing query identification can also help users to gain and achieve a better understanding of how the search engine and the ranking model maps their queries to the documents. And this in turn could result in higher transparency of search engines to the user. And we know that transparency is naturally related to the explainability, where the goal is that the user understands how and why a retrieval system or a recommender system returns a specific results. In our work, we put this step forward in the direction of transparency and propose a method to make the output of exposing query identification systems explainable. And our motivation for this is that to enable users to better understand why a query in the output of exposing query identification system might expose their given documents. In this regard, we formulate the task that we address as follows. Given a document and a retrieve and a ranked list of exposing queries, which is retrieved by EQI systems, we want to explain why these queries might expose the given document in the retrieval system. And in fact, we assume that such explanations could increase the usage of exposing query identification systems by providing transparency to those users and content creators on the web. To name a few examples and use cases of this, we can consider content creator risk awareness. In this usage, a user might not be aware of the consequences of the content they are about to publish and share on the social media. And providing an explanation about the retrieve list of exposing queries could help these users with an increased awareness about the potential exposure of their potential exposure of their publishing content. For example, an exposing query in the output of the EQI system could be semantically ambiguous or have several intents, and the given explanations could help the users to understand why the exposing queries would retrieve their contents. Another use case of explainable EQI could be considered when we use EQI as recommendation. In this use case, not only the user becomes aware of the risks of their documents, but also they get recommendation of possible modifications that can be applied to their documents to prevent it from being exposed by a specific query. Or we can consider it the other way around. to make it exposed to more relevant queries. Now, the thing is that the landscape of explainability in information retrieval is quite wide and full of diverse methods. Out of these methods, since our focus is on the explainability for the end user, for example, instead of search engineer, we use post hoc text-based explanation. To provide a text-based explanation solution, we follow the prior work, which use expansion terms for the purpose of explaining a ranked list of documents. In this approach, a set of expansion terms for a given query is showed to the user. And the idea is that to a user, the connection between a query and a document might not always be clear. For example, since we do not have any lexical match between the query and the document. But search engine, even in that case, could identify a document as a relevant document for a given query. The table in the above shows the query expansion model serving as an interpretable term-based ranking model, which mimics and imitates a complex document ranking model to be interpreted. Now here, for explaining the output of exposing query identification, in contrast to this prior work, we do not use expansion terms to explain a ranked list of documents, but instead, we expand each queries in the list of exposing query identification outputs to explain these outputs queries. And to this aim, we use the expansion terms from the two methods of RM3 and BO1. As an example, the table below shows a document and two exposing queries of this document together with their expansion terms. And we assume that the terms can indicate and show them, can indicate and show the user that the words of documents could have multiple meanings, and the search engine might expose the document to users who have a completely different intent in their mind. Now the question is that how evaluate these explanations? The thing is that while different measures can be used to evaluate explanations, we focus on the fidelity-based evaluation, and we specifically focus on formalizing the evaluation of fidelity for the explainability methods and leave other measurements such as comprehensibility and how well do the human understand the explanations for the future work. The prior work that I mentioned earlier on the explainability for document ranking have defined the fidelity as to the degree that explanations can replicate the ranked list for the original query. And they have used rank similarity measures such as RBO or Kendall-Tau. But in this regard, our goal is to explain a query queue in the outputs of EQI system in a way that the relevance and consequently the exposing status of a query for the document does not change fundamentally when the expansion terms are added to this query. And actually, we want that the results of the document retrieval systems on the expanded queries reflect the results of the systems on the original queries without explanations. And to this aim, we present two metrics for measuring the fidelity. For the first metric, to measure the fidelity of explanations to the original ranking results, we define a fidelity constraint based on the exposing status of a query with respect to a given document. And to formalize this constraint, we first define an indicator function, lambda, which shows the exposing status of a query Q for the document D, when we have ranking cutoff K for the ranked list of documents. Actually, lambda is equal to 1 if D is ranked in the top K ranked list of documents retrieved for query Q. Now, by using lambda, we can define a variable for capturing the change in the exposing status of the query, which we refer to as C. Now, the fidelity of the explained list of queries to the original list of queries in terms of exposing and status preservation can be formulated as this ESP equation in the middle of the slide. In this equation, mu is the user browsing model, and G is the fidelity gain for query retrieved for document D. And we specifically use this G as the user browsing model to discount the absolute fidelity gain and weigh the higher rank queries. And accordingly, the fidelity of the explained list of queries to the original list of queries, or whether to say the fidelity corresponding to document D, could be formulated as this final equation down in the page. And also, it should be noted that a normalization is applied to these values. And obviously, the final exposing and status preservation is estimated using an average over the fidelity of all documents in the test collection. Okay, we saw that the first proposed metric, ESP, captures the fidelity to the exposing status of each query. I mean, whether it is exposing or not exposing. But the thing is that it does not measure the degree to which the relative exposure level for document D with respect to different queries is preserved. I mean, ESP only counts for pointwise fidelity of queries and not for the fidelity of the explanations to pairwise and listwise order of exposing queries. For example, let's say we have a query 1, which ranks a document at rank 1, and query 2, which ranks the same document at rank 20. Now, if the expanded query 1 ranks the document at rank 20, and the expanded query 2 ranks the document at rank 1, and at the same time, if we assume that the ranking cutoff to determine whether a query is exposing or not is 20, both of these queries are still both exposing. But the thing is that the expanded version of query 1 and query 2 are downgrading and upgrading the level of relevance, respectively. And this is equivalent to not reflecting the performance of the systems on the original queries. Now, to account for such pairwise and listwise fidelity of explanations, we propose another metric, which we refer to as exposing order preservation, abbreviated as EOP. To measure the preservation of the relative exposure level of queries for the documents, we use the similarity between re-ranked version of the original query list and which we refer to as UD, and a re-ranked version of the explained list of queries, which we refer to as UDE. And then we use the Kendall-Tau correlation coefficient to measure the similarity between the two ranked lists of queries, UD and UDE. And we know that the Kendall-Tau correlation gives us a value between -1 to 1, where -1 indicates the perfect negative correlation and 1 shows the perfect match between the two ranked lists. And this is exactly what is described in this algorithm bomb, which shows the computation procedure of exposing order preservation metric for the test documents D. And obviously, the final EOP is estimated using an average over the fidelity of all documents in D. Regarding the experimental setup, since this work is the first one to study the explainability for EQI, we established the first experimentation, and we specifically use a benchmark and evaluate 3 retrieval models. The thing is that EQI experimental setup needs a large query set, and because of this, we use the fever data sets from peer benchmark, which consists of more than 1,000 queries, 100,000 queries. As to the ranking models, we use the two widely used dense retrieval models, ANCA and TCT-Colbert. And also we evaluate BM25 as one of the widely used traditional lexical rankers. To construct the test document sets, we first retrieve the documents for all queries using 3 ranking models. Then we select documents that are ranked at least one time for one query in the top key results list of a query. And then we aggregate the set of these documents and select those at the intersection of all 3 ranking models. And by doing so, we will have a single test collection across all models. Now we are going to answer 2 research questions. The first question is that what is the performance of the EQI models in terms of RELC when performing the query retrieval using expanded queries? This table shows the results of EQI in terms of RELC on both the original and the expanded queries. And as we can see, the RELC scores are around 0.5, which show that the retrieved queries are not completely the same as the truly exposing queries. Also, we can see that the EQI on queries expanded with both RM3 and BO1 result in a small improvement in the performance of EQI models for ANCA model. But in contrast to ANCA, EQI using expanded queries for BM25 and TCT-Colbert results in comparable performance to the situation where we use original queries. And the other thing that we can see is that EQI on the expanded queries with both RM3 and BO1 are comparable across different models. To better analyze this, we'll measure the similarity between the retrieved query list of the 2 methods for each ranking model. And for this, we use rank bias overlap as our similarity measure. And as we can see in this second table, the R view of the rank query is expanded with the terms from both methods of RM3 and BO1 have comparable EQI performance in terms of RELC. And why we see this, we can see that the retrieved query lists do not show high similarities across all values of rho, which is the top weightedness parameter of RVO. And actually, this shows that EQI method is not sensitive to differences in the expansion terms from these 2 expansion methods. The next question is, what is the fidelity of our explainability method in terms of exposing a status preservation? In this table, we can see the ESP fidelity scores with 2 settings of evaluation. The first one is based on only using, both using exposing and non-exposing queries. The second one is based on using only the exposing queries. And as we can see from the results in the E&E column, which corresponds to using both exposing and non-exposing queries, ANCA shows higher fidelity scores than BM25 and TCT-Colbert across all ranking cutoffs, and also with both with the expansion methods from both methods of R3 and BO1. This could mean that on average for documents in the test collection, ANCA is more robust to retrieval with the terms added to the queries by the expansion methods. The other thing that this table shows is the effect of non-exposing queries. Actually, the column in the right side of the table shows the number of non-exposing queries at each ranking cutoff of the EQI system. And as we can see, at higher ranking cutoff values, there are more proportion of non-exposing queries. Also, we can say intuitively that non-exposing queries are more robust in terms of changing the exposure status of a given document, as they have less relevance to the query. And we can use this to justify the increase in the fidelity scores based on the exposing status preservation at the larger ranking cutoffs in this table under the E&E column. Also, To better explore the effect of non-exposing queries, here we show the ESP fidelity scores based on only exposing queries under the E column. And as we can see, taking only exposing queries into account results in lower fidelity scores than when both exposing and non-exposing queries are used. And this could show the role of non-exposing queries in higher fidelity scores. The other thing that we can see is that in contrast to the results of exposing status preservation in the previous fidelity metric, with both exposing and non-exposing queries, Anke shows lower fidelity scores than BM25 Multistakeholder in terms of ESP with only exposing queries. And actually, this could mean that higher values of exposing status preservation with exposing and non-exposing queries for Anke's could be due to the exposing status preservation of Anke on non-exposing queries. The third question that we try to answer is what is the fidelity of our explainative method in terms of exposing order preservation. Here we can see the results of the 3 ranking models with expansion terms from RM3 and BO1 in terms of exposing order preservation. And as you can see, similar to exposing status preservation, Anke also shows higher fidelity than BM25 Multistakeholder when we perform EQI for the corresponding document retrieval systems. And this could again show the robustness of Anke to retrieval with the terms added to the queries with the expansion methods, as what we saw in the previous results. The other thing that we have here is the ESP and EOP results at different EQI ranking cutoff values for all ranking models. And we can see in the figure that in contrast to ESP, where the performance of the models increase at high ranking cutoff, in terms of EOP, the performance of models decreases in deeper ranks. And this could indicate that the difficulty of preserving the relative exposing level of queries in comparison to preserving their exposing status at higher number of queries at deeper ranking cutoffs, with deeper rank cutoffs. And finally, the other thing that we can see in the figure is that exposing and status preservation show less variability to the exposing query identification ranking cutoff, which is in contrast to exposing order preservation, which decreases with a higher, steeper steepness in lower ranks. And yeah, to wrap up briefly, I would like to mention that as the first work we addressed the explanation for EQI, and to the same we use query expansion as a form of explanation. And we propose an evaluation framework for measuring the fidelity of explanation in expansion-based methods. And finally, I would say that our work provides insights as to the challenges regarding the quantitatively assessing the quality of explanation in information retrieval systems. Thank you very much.
We are very glad you invited us to present the results of our user study. It's an exploration. It will be much different from the presentation style we just heard, just because of the very fact that the study we undertook is a fundamental research, a research based very much in the social sciences, psychology namely. And so the results that Linda Basso, a psychologist in training, Irina Nalis, this is me, I hold a PhD in psychology, and I'm a very happy interdisciplinary collaborator of Dr. Julia Neithardt, who runs as a director the Christian Doppler Laboratory for Recommender Systems at the University of Technology in Vienna. And what we did, we tried to find out relations between news diversity and well-being. And as I just mentioned, it is an experimental exploration, so very first steps towards the creation of recommender systems that could work on the results that we garnered by this study in regard to diversity-aware recommender systems in the news realm. I will briefly bring you through the problem statement and some related work, also give you some descriptions and definitions, of course. And then the main part will be on the contribution, the research questions, also the data source, the methods I will highlight, and of course the results. And I am very happy that for the final part of this presentation, discussion, and of course future work that we envision could probably also ignite some of the discussion here in this setup, in this forum. So happy to be here. And this is where our starting point is, working in this laboratory interdisciplinarily on recommender systems. We are very aware, we take this very serious, that news recommendations especially, so I think this entire workshop is dedicated to fairness questions, accountability questions regarding recommenders in all domains. Here we focus on the domain of news because it has been shown various times that news recommender systems do shape public discourse and have actual power to enforce behaviors that have a critical and oftentimes detrimental effect on democracies. So this is our starting point, and we believe that there are potentials that responsible news recommenders can have a depolarizing capacity once they go beyond accuracy measures, thus once beyond the typical repeating of the always same patterns of user behavior, but really promoting diversity, which is here in the center of our study. So yes, the preference-based news recommender systems can create, of course, there are people who do work to mitigate this risk, and there are discussions on filter bubbles, psychological filter bubbles, technological filter bubbles. So what we still believe is very important to work more and more on the increase of selective exposure, because it can undermine people's interest in news and their ability to cope with the content. Now, of course, the psychologist is speaking, but why do we see phenomena such as news will find me or other ways of news avoidance in the public? Because it is also related to questions of psychological well-being, of stress reactions that people try to avoid. So the challenge is to design humanistic, value-based news recommender systems to promote open debate and diversity. And what I also want to underline is that our research aligns strongly with the initiative of digital humanism, where we generally emphasize beyond accuracy and fairness in algorithms, and also where an interdisciplinary approach is very much appreciated. And altogether, we aim to enhance recommender system quality, promote fairness, and prioritize user-centric design. So on the next slide, I give you a brief definition and some insight into current studies on news diversity, which informed our study. So first of all, the importance of news diversity. It has been shown that it can protect readers from filter bubbles, should be vital for democratic societies, as it is enabling free public opinion formation by exposure to different viewpoints, diversity. For example, it has been shown in a very interesting research set up by Bernstein and colleagues that users' ability to critical thinking and problem solving can be positively shaped via news diversity. What is the role of recommender systems in this regard? As mentioned before, of course, they do shape public discourse and citizen perspectives. And as it has been shown that sometimes it has been done for detrimental causes and effects, yet now we also see the potential that by shaping responsible recommender systems, it is possible to balance individual user interests with algorithmic power meaning that in fact questions of also comfort or complexity reduction are also part of user interests. So there is, of course, a well-grounded reason why people also don't want to always see new stuff, but they also want to feel understood with their interests. And this is why some of the current accuracy measures still, of course, are valid. However, you should not go straight forward with this way of algorithmic power just because we have the big data, just because we have the knowledge of prior user behavior to continue that road. This is the part where we believe the role of recommender systems should and could be balanced better. Yet again, there are challenges in design. So to balance this user autonomy and the algorithmic operation is certainly no easy task. Again, there are questions of privacy. There are questions of very subtle psychological preferences ongoing. So achieving accuracy alongside their diversity in recommendations is, although it has been discussed in several years, there is a lot of talk on the beyond accuracy paradigm. I know many people here in the audience are familiar with it. Still, from what we see, there are still few studies working with real users and digging deeper into the psychological realm, which of course then relates to questions of democratic theories. Again, we also tried to be very careful in the definition on diversity itself. So when, and I will of course present it in a few slides from now, when we went via operationalization of our study design, how to actually choose what is news diversity, what are diverse sets of articles. There we went via democratic theories, how, for instance, the tone of the role mirrors different democratic perspectives. So there is already research that is built upon also political theories that needs to be taken very seriously. When what we actually aim for, you try to build proper and responsible recommender systems that do acknowledge people's needs and their behavior, but also their capacities in relation to a general idea of public value, democracy, and the role of media in it. And now a bit more on digital and the well-being, let's call it that way. There are few studies. Of course, it's also what we are very happy to see, an emerging field, but we believe that principles of information technologies and well-being are more and more looked upon as a integral or holistic, from a holistic perspective. And here I bring in a quote by the pioneer from MIT in human-computer relations. She's a sociologist and psychologist, Sherry Turkle, still active. And she researched since decades that in fact IT should and could uphold democracy, freedom of expression, questions of tolerance, diversity, but also complexity of ideas. Yet altogether, of course, this is no easy task. We're working with human beings, but that there is this responsibility, this is not a new find, to be honest. What is more and more coming into the focus of attention is questions related between the digital and the well-being, and the impact of digital technologies on individual and societal welfare are gaining interest, because ethical questions across various domains, especially healthcare, but of course also education, governance, media, have been and are being raised constantly. I'm not going now into the direction of, for instance, what you also see more in the public discourse this day, the relation, for instance, of teenagers and their well-being and social media, but this is the field where we are also closely relating our research to. So positive computing would be a way out, personalized human-computer interaction that takes into account autonomy and self-determination, and really to take challenges like data privacy, but also when it comes to health questions, patients' autonomy or equal access into a very serious accountability, which is of course also part of that workshop session. Nevertheless, well-being is not an easy single item construct. Human well-being within the field of psychology, it has been studied under very many names. There's from also well-being and any other subjective well-being constructs of this multifaceted approach. However, it's always related, no matter which name you find it under, related to subjective well-being, and also a question of positive development. So when I say development, this also entails that well-being is not a one single time point question. It's nothing that is not to be changed. Of course, it can be influenced. It can be influenced for the worse, for instance, with news, but for the better. And that there is this quest for society, but also for us as researchers to create environments where positive development in human well-being is enabled. So where do we derive our hypothesis from? It was that body of research, and the two main research questions or hypotheses, I'm sorry for this typo here, is the relation between news recommendation and well-being was the first focus. And there we postulated that diverse news recommendation could increase users' subjective well-being. And the second hypothesis was that the relation of diverse news with user satisfaction could also be increased. Two hypotheses we tested via a study that consisted of 3 parts. So there will be, as I already said in the beginning of this talk, no technical evaluations, no coding, or very little of it was involved of it. We went via an initial questionnaire. Altogether, we set up actually an online survey, and there we presented participants with a questionnaire, an experiential setup, so randomized 2 groups of participants, where these participants were asked to interact with different types of news recommender systems, and then this was followed by an exit questionnaire. More on this in a second. The main goal was to answer the question, how do diversified news recommendations influence users' subjective well-being? And this web-based controlled experiment with an independent sample of altogether, after excluding several participants for various predefined reasons, we ended with a sample of 90 people, which might not sound a lot, but on the other hand, we actually went via a G-power test, so we could go with testing the 2 sets that were presented, and it was articles presented to participants, and the categorization of diversity, I also hinted at this, was based on very specific questions of topic plurality, in tone, and we also applied a survey on the brief inventory of thriving scales, thriving as one of the words that is being used simultaneously in parallel with other words like well-being. So this was the well-being scale we actually used. And to give you an idea of the survey structure, especially the meaty part, the article choice, the one that would eventually be translated into actual real-life recommender systems. These articles were derived from the cooperation our lab has with the Falter, which is a weekly political magazine in Austria, Vienna. And there we could work from a set of altogether 1,272 articles. And those articles differed in political viewpoints presented, the journalistic writing style, which was used, the language, for instance, was it more neutral, more objective, direct speech, emotional. And there was also a difference to be understood via the perspectives that we're taking, if it was more on the negative, more the positive aspects. Also, the more factual, let's say, criteria like the genre in the newspaper, because I think we can all agree that it probably makes a difference if you read something on culture, the next movie, which of course can be emotionalizing, but probably won't lead you so much in a problematic filter bubble as, for instance, coverage on economic problems, just as one trivial examples. And we also were able to differentiate the articles in regard to the locations they reported off, like Europe, Vienna, or worldwide. And here in German, which was the language in which this study was undertaken, group 1 is shown 3 pages with a diversified set of items. So there we applied those criteria by Hellberger. And group 2 was shown 3 pages with what we, from those criteria, could understand or thought to be a non-diversified set of articles. And then the participants were asked to read through all the articles, select the one they would most likely read. So here's an example of this. And I also mentioned that we set up an online study, which was actually online survey. Here, 2 more words on news diversity and the brief inventory of thriving scale. So these were the parts in the beginning and the end of the study, which was presented as a questionnaire for all participants. First, in the entrance section, after demographic questions, we also asked participants to report on their media consumption in general and their personal attitude towards the necessity and importance of exposure to different viewpoints in the media. So in fact, the participants were not pre-selected. When we did our snowballing to invite the participants, they were not knowing what kind of study they would participate in. Nothing was mentioned about news, and of course, nothing about recommender systems or news diversity in detail. However, when we started, we wanted to make sure that, in fact, we want also, before the participants go via the diversified or non-diversified set of articles, to tell us their viewpoints of it. On the results later. And the brief inventory of thriving is a self-reporting measurement, so a very typical way to work in the realm of psychology. It's a construct that refers to optimal functioning, positive development in various domains of life, which, as we will see later, was somehow a problem or a limitation of our study. However, it is a very well developed tool, which originally was also on good grounds that we used it for that study. However, it will show as a limitation. So now, as I already lowered my voice or kind of hinted at some problems with our study, the result of those independent t-tests, so it was not statistically very sophisticated. We had 2 groups, so we had all other tests. We performed all other necessary tests and checks before to make sure that independent t-tests are possible to perform. It was okay to do so. But now, and this is why I really want to thank once more the organizers of this workshop, that we are able to present in this context of discussion, of advancing research, something that you don't see often in peer-reviewed journals, where you cannot usually publish non-significant results. Here we had this unfortunate situation that neither hypothesis 1 nor hypothesis 2 yielded significant differences. So here you see that for H1 needed to be rejected because in the subjective well-being scale, both groups had almost the exact standard deviation. And also the question on user satisfaction, would it be increased the satisfaction with diversified recommendations? There also we did not find a significant difference between the 2 groups, and the experimental group did even score lower than the control group. So what about this, and why are we still believing that it's valuable to show this? The limitations, first, there are many, of course, methodological flaws or limitations that can be fixed easily. This, for instance, as it was a very first exploration into those constructs, it was cross-sectional only. Of course, if you would go via longitudinal study, which maybe also applies methods in psychology, for instance, a diary study where you could even monitor over a short period of time, but with many different measurement points, let's say towards through 1 month, you could certainly better monitor what the well-being of participants is in general, but also in regards to the actual media consumption. in regard to the media consumption. I gave away that we had trouble with this BIT scale, so to say. The brief inventory of thriving is a well-established scale for subjective well-being. There was no problem in that realm. However, it is not specifically dedicated for digital media-related well-being assessment. And it was very interesting for us also to see that nothing of this was available. And then something that we also see in psychology a lot, there was, of course, user self-selection for participation and all those questions of pre-existing support for diverse news consumption may have also led to biased results. Altogether still, and now I'm already on the pre-last slide, we did not find significant positive impact on subjective well-being or satisfaction, yet we still believe that it is a fruitful avenue to investigate in the future. And here I also highlighted from the first questions in the questionnaire in the survey, where we asked participants what they think of diverse media. It might have also be question of socially a bias that people think they need to answer that way. Yet I think it also mirrors that when people say they recognize the importance of value-based media, they also ask for it. And so although our study setup, but maybe also some other problems that we will encounter in the future by researching those questions, will still yield critical results. I'm very open to learn more about that in the future, but we still believe that, for instance, via longitudinal studies for news diverse recommender systems, we can find ways that really can increase well-being and improve the general recommendations we do in news. And for other parts, very psychologically specific, like controlling general well-being, developing specific skills, investigating psychological aspects. I will not go too much into details, but of course, there's always ways, which I hope many of you will pursue in the future, despite the difficulties, to really go via user studies. So I thank you for your attention, and I'm happy to answer questions.
I'm Sejino. I'm a PhD candidate in Georgia Tech. And today I'm happy to introduce our paper, Stabilizing Recommendation by Rank Preserving Fine-Tuning. So we all know that existing deep learning models are vulnerable to input data perturbation by the adversarial attackers. This is a very famous example about the panda image. If you add the adversarial noise to the image, then their classification result is flipped to even, which is not desired. There can be also adversarial rotation. If you just rotate the image, then also the classification result is again changed. But how about the recommender system? Are they robust and stable against the adversarial attack? Do they produce stable recommendation against the input perturbation? That's our main research question here. But we need to think about why do we care about this model stability. And this is like very important task in terms of like drug recommendation, finance recommendation, housing recommendation. Those are our high-stake application of this problem. And so like unstable recommendation can be very disruptive and dangerous to users for those high-stake applications. So let me give you an example about the drug recommendation. So imagine you're a patient and you're receiving a drug recommendation based on your electrical health record. And imagine there's another patient which is unrelated to you, and there's somehow some noise to this health record of this unrelated user. It can be like random noise to this record. And due to this random noise or perturbation to another unrelated user, now your drug recommendation result is totally changed. Then there can be like some unrelated drugs in your recommendation. Then if you just naively take the recommendation, then it can be even dangerous to your health. So it's very important to develop stable and trustworthy recommendation against these minor input perturbations, or even like major one too. So let's think about the like perturbation setting. in this paper, we are talking about interaction perturbations here. So you can think some interactions can be deleted, injected, or some can be replaced with other items. And so what happens to recommendation if like few of the training interactions are deleted? Then the recommendation model is retrained with this perturbed data, and they produce the output. And if the output of this new retrained model is totally different from the original recommendations, then we say this model is unstable. And our goal is we want to make this model more stable. But how can we do that? So we are proposing a fine-tuning approach to enhance the stability of recommender system. But let's see the first, like the top part first. So if in the figure, in the top part, you can see the original trained data, and there can be multiple interactions of the users. They are fed to the recommendation model, and the recommendation model is trained with these interactions. And they generate the recommendation for all users for instances. So we call it this recommendation result and the original recommender as like reference, which will be used later. But if you see the bottom left here, you can see the perturbations. And we already assume this like interaction level perturbations. So you can see some of the new interactions are injected to the original trained data. With this new data, the recommendation model can be retrained, and without any fine-tuning or any prevention, then they will just generate very unstable recommendation, like the figure in the middle. Compared to the original recommendation, their results are totally different. And in this case, this middle model, this base model is unstable. But we are proposing a special fine-tuning approach, which is called finest, that can be applied to any recommenders. And with our fine-tuning approach, the final recommendation results are very similar to the original ones. In this case, our final model is very stable. So this is our main research question, main research statement. How can we build a stable recommendation model by fine-tuning? So we are proposing a method called finest, which can be applied to any sequential recommendation models. And how can we stabilize the model? We are doing some fine-tuning, even for the deployed ones. There are 5 different steps in our fine-tuning method, finest. The first step is very simple. We are just obtaining reference length list, which is just like the output of the given recommendation model. So the given recommendation model, they are trained with the original trained data, and they generate the output for like all users or all training instances. And this step 2 to step 5 is actually our fine-tuning step. And if you see the step 2 first, we are simulating the future perturbations. So we don't know what exact perturbation will be done in our data in the future. So we are simulating all the possible perturbations. Because we are assuming interaction level perturbation, during this simulation, our choices are straightforward. Either it's injection, deletion, or replacement. So they are either like sample among like with the uniform probability. So in this epoch first, it can be either injection, or like in the next epoch it can be like deletion. In the like next epoch it can be replacement. So let's say in the example we are talking about the injection perturbation. So with this perturbed data, the third step is very also standard. We calculate the recommendation loss function, which is like just the simple standard loss function of the given recommendation model. And the fourth step is our major contribution, which is computing rank preserving loss function. And the main intuition of this rank preserving loss function is that if the current recommendation results are totally different from the original reference rank recommendation, then we are going to minimize this rank preserving loss that can actually make the model mimic the original recommendation result. So this, specifically this rank preserving loss, do the pairwise comparison of the original rank list and our current rank list. So let's say if you see the first rank list and the first rank here, then if you see a lot of changes, then this rank preserving loss will be very high. Then if we minimize the loss, then eventually the final fine-tuned model will produce very similar linked list to the original reference linked list. And this fine-tuned model is also able to generate very similar linked list to the reference one, even against the input perturbation. So if you iterate this process, step 2 to step 5, several epochs, then your recommendation model will be very stabilized. So you may wonder what's the rank preview loss exactly. So this figure is helping you to understand the loss. So if you see the top part, there's a ranked list of the single interaction. So in the ranked list, there are multiple items. And ideally, we want to preserve the ranks of all items. And in that case, the robustness will be perfect against the attack. However, that's not feasible because preserving the ranks of all items is very expensive operation. So instead of that, we are just preserving the ranks of top K items, because top Ks are most important to users because they are displayed to the user. And especially also just preserving top K's ranks is much cheaper compared to preserving the ranks of all items. Then the natural question is, how can we preserve those top K items ranks? So there are two components in our rank preservability loss. The first component is about preserving the ordering of the items. And the second component is how to make the probabilities higher than the top K plus 1 to 2K. So let's first see the first component. So this first component is the preserving the ordering of top K items. So the probability of this first top 1 item should be higher than the probability of the top 2 item. That's the first inequality. And if you see the next inequality, you see the same thing. The top 2 items probability should be higher than the top 3 item probability. So this is very straightforward. But is it enough? No, because even if you satisfy all of these inequalities, their row probabilities can be still lower than the other items' probability. So that's why we need another constraint, which is we want to make sure that their top K probabilities are much higher than other items' probability. So we did a pairwise comparison of these probabilities. So the top 1 items probability should be higher than the top 4 items probability. And if you do the pairwise comparison for all the top K items, then we can make sure that we preserve the ordering, and also we also preserve the high probability of the top K items. So by using those two components, and after fine-tuning, the model is actually producing almost identical top K items compared to the reference linked list. If there can be some differences in other places, not top K, but they are not important to the user, so they are usually ignored, so they are not our main interest. We focus on the top K. So this was the methodology, and let's check about the experimental results. We used the 3 different data sets, Last.fm, Foursquare, and Reddit, and we also tested the state-of-the-art recommendation models, stability, TSS-Reg, Buffer-Reg, and LSTM. And we test our fine-tuning performance against these 2 different input data perturbation, random and Casper. Casper is the state-of-the-art. And we also tested the several baselines, like adversarial training and ACAA, and so on. This is the main experimental result on the Last.fm dataset, which is the largest. And across all the input perturbation, across all the recommendation model, our fine-tuning method is actually able to boost or increase the stability of the recommendation model. So if you see the columns here, you can see the RBO and Jacquard. Those are our stability metrics. So those are between 0 and 1, and higher means the model is more stable. So higher is better. And across all the columns, you can see that all the stability metrics are increased with our finest method. And if you see the bottom left figure, and across all the data set, this table is only for the last FM dataset, but of course for the dataset, we also see the increased servability of the models. And the last figure is the interesting one, because if we increase the training data perturbation ratio from 0 to 10%, 10% is really large perturbation to the data set. Even with this large perturbation, our finest methods still increase the stability of the model. So in this paper, we presented a novel fine-tuning method that can be applied to any sequential recommendation models. And it can increase the stability of the recommendation models. And we also show that existing recommendation models fine-tuned with our model show higher stability, and also they preserve the recommendation accuracy, which is also desired. So our future work includes how can we extend our work to diverse perturbation, not just the interaction perturbation. So there might be some embedding-based perturbations. And we also want to extend our method to non-sequential recommendation models, such as like matrix factorization based. Oh yeah, so I want to keep it short, so let's have a Q&A time.
Hello everyone. So this is joint work with the Multistakeholder, and Emilia Gomes. We're with the Joint Research Center as is part of the European Commission. And this is also part of the series of papers and work that is connected to this project that is called AI, but I will talk a bit about it in the end. So, well, what did we want to do with this? We wanted to look at the diversity of our own community. So this is sort of an introspective, a preliminary one still. So the motivation is diversity is fundamental to working with the system. We've been hearing about diversity pretty much already here. And the rationale is that the permission filtering should not disturb or exclude important elements of the real world. And under this perspective, one of the best ways to do this, to achieve this, is to involve diverse views in the design and development of the recommender systems and the systems themselves in the first place. This is referred, for example, when using legislation and future legislation in principle. So we picked up on the geographic diversity because we felt it was one of the most important dimensions, and also because it's one that is easy to measure, from which we have data. And before talking about the data, I was a bit lazy when I started this presentation, so I just added this to the motivation. This is a paper by Lorenzo, it's the first author. So this is to explain a bit the title behind recommender systems. So even if it's always crucial to look beyond, which is what we did in the research, what happens when we look behind? Who's researching and developing? So we analyzed the proceedings of the past 15 years with Recsys to get an idea. And what we can find. So we look at the geographic diversity, what data we choose, we went to scope, we just search for the proceedings with Recsys. Between 2007, which was the first edition, and until 2022, we found 1,042 papers and more than 4,000 unique multi-year pairs. Okay, so some authors are repeated every year, so they are not unique. The country was extracted from the author affiliation, so this is not the nationality or the country of birth or anything else. This is the country of affiliation. And we had to manually correct about 50% of the data because affiliation is quite noisy. I don't know if you're aware of that. There are people with double affiliation. Don't put the country, put this in the US state, for example, or sometimes California, it's Canada, and stuff like that. So this is not to brag that we did all this manually. This is just to let you know that although we did this correction, there is still some noise in the data. We did not think it was significant. So we have a list of the conferences here and the format, and you clearly see that the number of authors is increasing, fortunately. And the distinct countries also been increasing, although they achieved more or less stability since 2017. So with a bit of acceleration. For the diversity metrics, use the Untitled Index. I don't pronounce this well, but also actually this metric is a concentration metric, so we use the inverse to measure diversity. Okay? And the Shannon index. The accomplishment is also known as Simpson. What my college here probably as Simpson index. So I will not go through this. We implement these questions later. So going straight to the results. Only 9 countries are within the top 5 contributors in at least one edition. So we have this list of 9 countries, and to be in this list, they have to be the top 5, the country with top 5 authors in any edition. This list. And only China and Israel are not from weird countries. This weird acronym means Western, educated, industrialized. I don't remember. I will remember. Yeah. Reach and development. Something like that. Authors from this group contributed between 65% and 85%. And the USA, this isn't, I guess it's not a big surprise. USA is by far the most prevalent country and oscillates between 21% in 2013, where it was, and 44% in 2014. This was in Silicon Valley. We also looked at countries that are considered economically developing, and the definition that we use is the one that is used by ACM to provide support in discount rates conferences. And these countries contributed between 1% in 2009 and 22% in 2020. In 2020, it was fully online. The prevalence is from BRICS, another acronym, which means Brazil, Russia, India, China, and South Africa. And as you might expect, the most prevalent country is China. So no big surprise. In terms of the diversity metrics, we can see that they're not greatly impacted. I wanted to say something else here, but I forgot to put it in the slide. There is a slight increasing trend. At least visually, you can see sort of an increasing trend, which is a nice thing. However, this does not reflect greatly in the metrics that we're using. There is maybe a slight, if you look very well, maybe you can see a slight increase in the Shannon index. And besides this, what we observe from here is that Minnesota and Silicon Valley have been the least diverse. And Hong Kong and Como have been the most diverse. Conclusions. Diversity is still rather low. 2/3 of authors come from only 9 countries, on average. Pick up all the contributions that have been done so far to the Recsys proceedings. 2/3 of the authors come from only 9 countries. There's a slight increase in participation from economically less developed countries, but this is still a bit premature to attribute this at least alone to efforts that we've been, as a community, we have been conducting to improve on diversity. And this is, well, what this shows is basically that these efforts are necessary and maybe should be important. About future work, because this is very preliminary work, we want to look at the type of affiliation, we actually already started to do this. The researchers come from academia or from the industry or from governmental bodies like myself. Also topic diversity in gender, although this is complicated because the data that we have is from the proceedings. It's hard to infer gender from the names, especially for non-Western countries. Although there are good IPTS to do that. Those 15% that we check by hand, if you go to names, will likely increase the devices value. And also you want to check on the intersections between these interactions. What we can see from that, for example, it's pretty obvious that US contributions are at a big part from the industry, maybe from Europe not so much. I don't know. This is just an example. And that's pretty much it. I also invite you to check the project website. So basically, this project, as I said, we already have. Well, not myself because I've done it recently, but there are a few papers from other communities that you can check. And our objective is the website is a bit outdated, but our idea will be to update it in a more systematic way, at least with the most simple statistics about the number of conferences. So that's it. Thank you very much.